At the core of every swirling galaxy lies a monster so powerful, it bends the very fabric of reality around it. Picture an invisible beast with the weight of millions of suns, capable of ripping stars apart and twisting time itself. This isn't science fiction, it's the supermassive black hole, nature's most terrifying and fascinating mystery. Today, we're going deep into the cosmic abyss to uncover 50 mind-blowing secrets about these gravitational giants. From the way they warp space to the strange connection they might have with dark matter, each revelation will change how you see the universe. Think of us as your guides on this journey to the edge of understanding, where even light can't escape. By the time we're done, you'll know why scientists stay up at night puzzling over these cosmic puzzles. So buckle up and prepare to have your mind stretched like space-time near a black hole's event horizon, because what we're about to reveal will leave you seeing the night sky in a whole new way. And here's a taste of the strangeness to come. Some of these black holes spin so fast they drag the entire universe around with them. But that's just secret number 3 out of 50. You ready to dive in? Let's peel back the first layer of this cosmic mystery. Imagine something so massive it could hold entire galaxies together, yet so dark it vanishes against the blackness of space. That's the paradox of supermassive black holes. They're the invisible titans ruling from the shadows. Here's the wild part: we've never actually seen one directly. No telescope can photograph a black hole's true form because, by definition, nothing escapes it, not even light. So how do we know they exist? We watch their gravitational bullying. Stars near a galaxy's center don't orbit peacefully. They whip around at dizzying speeds like marbles caught in a whirlpool. That frantic dance betrays the presence of an unseen monster pulling the strings. Gas clouds, too, spiral inward, heating up until they scream in X-rays. A dead giveaway. Now, let's talk scale. A typical stellar black hole, the kind formed when a star collapses, might weigh 20 times the Sun. Impressive, right? But supermassive black holes laugh at those numbers. The smallest are millions of solar masses. The heavyweight champs think billions. Take Ton 618, a leviathan so vast it could swallow our solar system whole and still have room for dessert. But here's what really twists your brain. These titans don't just live in galaxies, they shape them. Their gravity dictates where stars form and how fast. A quiet black hole might let a galaxy flourish, while an overactive one can blast away star-making gas with terrifying jets. It's a cosmic balancing act we're only beginning to understand. So remember, when you gaze at a galaxy's glowing core, you're seeing the aftermath of an invisible god's work. And this is just secret number 1. Buckle up, the rabbit hole goes much deeper. Now let's journey back to the very beginning, because the origin story of these cosmic giants is just as mysterious as their nature. If supermassive black holes are the invisible titans ruling galaxies today, how did they get so powerful so fast? That's the million-dollar question, and astronomers are still piecing together the puzzle. One leading theory suggests these monsters were born from the direct collapse of primordial gas clouds in the early universe. Picture this: vast, dense clouds of hydrogen, untouched by stars or galaxies, collapsing under their own gravity. No star death, no fireworks, just raw, unfiltered collapse into a black hole seed hundreds of thousands of times the Sun's mass. It's like skipping the toddler phase and jumping straight to adulthood. But here's the twist. Other scientists argue these black holes started small, as stellar black holes left behind by the first generation of massive stars. Over time, they gorged on gas, merged with others, and ballooned into the supermassive beasts we see today. The problem: time. Some of these black holes existed when the universe was less than 1 billion years old, cosmic infancy. Growing that big, that fast, is like trying to bake a wedding cake in 5 minutes. The math doesn't quite add up, and then there's the wild card: supermassive stars. These hypothetical behemoths, hundreds of times heavier than any star today, could have collapsed directly into black hole seeds without the usual supernova drama. Think of it as a cosmic shortcut, a backdoor into creating something massive almost instantly. The real head-scratcher: we've spotted quasars, bright, active supermassive black holes, shining when the universe was just 700 million years old. How did they have time to form, let alone grow so brilliant? It's like finding a skyscraper in the middle of an ancient wilderness with no construction crew in sight. So which theory wins? The truth might be a mix of all three, or something we haven't even imagined yet. What's clear is that these black holes didn't play by the rules we know, and that's what makes them so fascinating. Every discovery peels back another layer, revealing just how little we truly understand about the universe's darkest architects. And this is just secret number 2. The deeper we dig, the stranger it gets. Now, let's unravel another cosmic enigma: the spin of supermassive black holes. Picture a spinning top, but on a scale so vast it bends the fabric of spacetime itself. Some of these giants whirl at nearly the speed of light, while others barely rotate at all, and this dizzying difference holds clues to their chaotic pasts. Take a black hole spinning at close to light speed. That kind of velocity doesn't come from nowhere. It's the result of a violent, messy life, like a cosmic pirouette fueled by endless feasts. When gas and stars spiral into the black hole, they don't just vanish. They swirl around it, adding momentum like a whirlpool sucking in water. The more it consumes, the faster it spins. Some supermassive black holes have been dining non-stop for billions of years, their spins revved up to the universe's speed limit. But then there are the sluggish ones, black holes that barely rotate. These might be the cosmic equivalent of picky eaters. If a black hole gulps down matter haphazardly, with gas and stars falling in from random directions, their opposing forces can cancel each other out, leaving the black hole with little spin. Or worse, imagine two black holes colliding. If they merge at odd angles, their spins can clash, leaving the newborn black hole slower than its parents. It's like two ice skaters grabbing hands mid-spin. Sometimes they end up tangled and nearly stationary. Here's where it gets even stranger. A black hole's spin isn't just a curiosity, it shapes its surroundings. A fast-spinning black hole drags spacetime around it, twisting magnetic fields into powerful jets that shoot out matter at nearly light speed. These jets can stretch for thousands of light years, lighting up galaxies like cosmic lighthouses. Meanwhile, a slow-spinning black hole is quieter, its influence more subdued. But the real mystery: some supermassive black holes shouldn't spin as fast as they do. Even with endless meals, physics says there's a limit to how much they can speed up. Yet, we've spotted some defying that rule, spinning faster than theory predicts. Maybe they're merging with other black holes in just the right way, or perhaps there's a hidden process we haven't discovered yet. What's clear is this: every black hole's spin tells a story. It's a record of collisions, feasts, and cosmic violence written in the language of gravity. And just like fingerprints, no two spins are exactly alike. The next time you ponder these dark giants, remember their rotation isn't just a detail. It's the key to decoding their wild, untold histories. Now, let's turn our attention to one of the most violent and spectacular events in the cosmos: the moment a star strays too close to a supermassive black hole. Imagine a star, billions of years old, living out its life in the relative safety of its galaxy. But one wrong move, one unfortunate orbit, and it's suddenly caught in the grips of an invisible monster. What happens next is a cosmic spectacle so intense it lights up entire galaxies. When a star ventures too near a supermassive black hole, it doesn't just get swallowed whole. Instead, the black hole's immense gravity stretches and tears the star apart in a process called a tidal disruption event. Think of it like pulling a marshmallow apart, except this marshmallow is a massive ball of gas and plasma, and the forces at play are unimaginably stronger. The side of the star closest to the black hole feels a much stronger gravitational pull than the far side, creating a tidal force that rips it to shreds. As the star is torn apart, its material doesn't vanish immediately. Instead, it forms a swirling, chaotic disk around the black hole, heating up to millions of degrees and unleashing an enormous burst of light, often outshining the entire galaxy for weeks or even months. Astronomers call these flares cosmic lighthouses because they reveal the black hole's feeding habits in vivid detail. Some black holes gulp down the debris quickly, producing a short, intense flare. Others take their time, nibbling at the star's remains and releasing energy in longer, slower bursts. But here's the fascinating part: no two tidal disruption events are exactly alike. The size of the star, its composition, and even the angle at which it approaches the black hole all shape the outcome. A small, dense star might put up more resistance before being torn apart, while a bloated giant could disintegrate almost instantly. Sometimes the black hole's spin plays a role too, warping the debris disk and altering the flare's brightness. These events don't just make for dramatic cosmic fireworks, they're also gold mines for scientists. By studying the light from these flares, astronomers can measure the black hole's mass, its spin, and even the behavior of matter under extreme gravity. It's like getting a backstage pass to the universe's most extreme physics lab. And yet, despite all we've learned, mysteries remain. Some tidal disruption events produce unexpected jets of plasma, shooting out at nearly light speed. Others flare up again months or years later, as if the black hole left leftovers on its plate. What's clear is that every time a star falls victim to a supermassive black hole, it leaves behind a trail of clues, each one helping us piece together the hidden rules of these dark giants. So the next time you look up at the night sky, remember, somewhere out there, a star might be meeting its spectacular end, lighting the way for us to uncover the secrets of the cosmos. Now, let's shift our gaze to one of the most jaw-dropping displays of power in the universe: relativistic jets. While tidal disruption events show us the destructive side of supermassive black holes, these jets reveal something even more extraordinary: their ability to launch matter across cosmic distances at nearly the speed of light. Picture this: a black hole, often millions of times more massive than our Sun, hurling twin beams of superheated plasma so far that they stretch beyond entire galaxies. These aren't just random bursts, they're precision-engineered cosmic accelerators, and they hold secrets about how black holes interact with their surroundings. So how do these jets form? It all starts with the swirling chaos of the black hole's accretion disk. As matter spirals inward, it doesn't just vanish. Some of it gets channeled outward along the black hole's poles, propelled by unimaginably strong magnetic fields. Think of it like water spinning down a drain, but instead of going straight in, some gets shot out through a pair of high-pressure hoses. These magnetic fields act like cosmic slingshots, twisting and accelerating particles until they're moving at 99% the speed of light. That's so fast, a jet could cross the entire solar system in less than a day. But here's where it gets even more fascinating. These jets aren't just straight lines, they're dynamic, twisting structures that can extend for thousands of light years. Sometimes they even curve or wobble, leaving behind glowing trails of radiation that light up the surrounding space. The energy packed into these beams is staggering, often outshining every star in their host galaxy combined. And because they're so energetic, they serve as natural laboratories for studying physics under conditions we could never recreate on Earth. One of the biggest mysteries is why only some supermassive black holes produce these jets. Scientists believe it's connected to the black hole's spin. The faster it rotates, the more efficiently it can power these cosmic beam cannons. Magnetic fields play a starring role too, acting like giant rubber bands that store and release energy. When conditions are just right, the black hole taps into this magnetic reservoir, launching jets that can influence entire galaxy clusters, heating up surrounding gas and even shutting down star formation. These jets don't just dazzle astronomers, they shape the evolution of galaxies themselves. By studying them, we've learned how black holes can act as cosmic regulators, their reach extending far beyond their event horizons. And every time we detect a new jet, whether through radio telescopes or X-ray observatories, we get another piece of the puzzle, another clue about how the most extreme objects in the universe wield their power. Now, let's turn our attention to one of the most dazzling cosmic phenomena, quasars. These brilliant beacons, shining from the farthest reaches of the universe, aren't just distant stars or exploding galaxies. They're supermassive black holes in their most ravenous, energetic state, gobbling up matter so fast that they outshine everything around them. Picture a black hole so voracious that its feeding frenzy creates a glow visible across billions of light years. That's the power of a quasar. What makes quasars truly extraordinary is their sheer luminosity. A single quasar can emit thousands of times more light than an entire galaxy, all from a region no larger than our solar system. This mind-bending brightness comes from the superheated material swirling into the black hole's accretion disk, where friction and extreme gravity heat it to millions of degrees. The result, a blinding torrent of radiation, everything from X-rays to radio waves. That makes quasars the ultimate cosmic lighthouses. But here's the twist: quasars aren't just bright for the sake of it. Their brilliance reveals a black hole in the midst of a growth spurt. When a supermassive black hole finds itself in a gas-rich environment, it feasts relentlessly, pulling in vast amounts of matter. This feeding frenzy doesn't just produce light, it also generates powerful winds and jets like the ones we explored earlier. In fact, many quasars are accompanied by those spectacular relativistic jets, adding to their already staggering energy output. What's even more fascinating is that quasars are cosmic time capsules. Because light takes time to travel, the most distant quasars we observe are actually relics from the universe's youth, some dating back to when the cosmos was less than 1 billion years old. These ancient quasars pose a puzzle. How did supermassive black holes grow so massive so quickly? It's a question that challenges our understanding of black hole formation and the early universe. Quasars also play a surprising role in shaping their surroundings. Their intense radiation can heat up gas across entire galaxies, stifling star formation and effectively putting a brake on galactic growth. In this way, quasars aren't just passive beacons, they're active participants in the evolution of galaxies, wielding influence far beyond their immediate vicinity. Today, most quasars we see are relics of a bygone era, when the universe was denser and black holes had more fuel to consume. Modern galaxies like our Milky Way harbor quieter, supermassive black holes, their quasar days long past. But by studying these brilliant objects, astronomers gain invaluable insights into the violent, energetic processes that shape the cosmos. Every quasar we detect is a window into the universe's most extreme environments, and a reminder of just how dynamic supermassive black holes can be. Now, shifting our gaze closer to home, let's uncover the enigmatic presence at the very center of our own Milky Way, Sagittarius A star. Unlike the dazzling quasars we just explored, this supermassive black hole is surprisingly subdued, almost like a cosmic recluse. But don't let its quiet demeanor fool you. Sagittarius A star holds secrets that are reshaping our understanding of black hole behavior. First, let's put its size into perspective. Sagittarius A star packs the mass of roughly 4 million suns into a space no larger than Mercury's orbit. That's an astonishing concentration of gravity, yet it emits only faint flickers of light compared to its more active counterparts in distant galaxies. Why is ours so calm? The answer lies in its diet, or rather, its lack of one. Unlike quasars gorging on gas clouds, our black hole survives on meager cosmic crumbs, with only occasional snacks of passing dust or gas. The Event Horizon Telescope's groundbreaking image of Sagittarius A star in 2022 revealed its shadow, a dark void encircled by a fiery ring of bent light. This eerie silhouette matched Einstein's predictions perfectly, proving that even quiet black holes warp spacetime dramatically. But here's the puzzle. The ring around Sagittarius A star was fuzzier and more asymmetrical than expected. Scientists believe this could hint at turbulent magnetic fields or an uneven flow of infalling matter, clues that our galactic center isn't as serene as it seems. Another mystery is its sporadic flares. Every few hours, Sagittarius A star burps out bursts of X-rays, brightening momentarily before fading back into obscurity. These flickers suggest small pockets of material are being violently heated as they spiral inward, offering us rare glimpses into the chaos just outside its event horizon. Some theories propose that hidden reservoirs of gas or rogue asteroids might be fueling these mini outbursts, but no one knows for sure. What truly sets Sagittarius A star apart is its role as a cosmic laboratory. Its proximity, just 27,000 light-years away, lets astronomers study details impossible to observe elsewhere. For instance, researchers have tracked stars like S2 whipping around it at blistering speeds, their orbits serving as a direct test of general relativity. One such star recently completed its 16-year loop, its path bending exactly as Einstein foretold. Yet the biggest surprise, our black hole's silence might be temporary. Evidence suggests Sagittarius A star had a quasar-like outburst a few million years ago, lighting up the Milky Way's core. Ancient gas clouds nearby still bear the scars of that long-ago feast, glowing faintly from the afterglow. This means even the calmest supermassive black holes can awaken, and when they do, their fireworks redefine their galaxies. So while Sagittarius A star may seem like a gentle giant today, it reminds us that black holes, much like sleeping volcanoes, have dormant phases and eras of fury. Its quiet presence offers a front-row seat to unraveling the life cycles of these cosmic titans, one careful observation at a time. Now, moving deeper into the cosmic puzzle, let's confront one of astronomy's most persistent mysteries, the case of the missing middleweights. If supermassive black holes are the sumo wrestlers of the cosmos, and stellar black holes are the lightweight contenders, where are all the intermediate-sized fighters that should bridge the gap? This is the missing link problem that has astronomers scratching their heads. The universe appears to have skipped a weight class. On one end, we have stellar black holes, formed when massive stars collapse, typically weighing between 5 to 100 times our sun's mass. On the other, supermassive black holes dominate galactic cores with millions to billions of solar masses. Logically, there should be a population of intermediate mass black holes, those ranging from a few hundred to a few 100,000 solar masses, acting as stepping stones between these extremes. Yet they remain frustratingly elusive. Why does this gap matter? These middleweights could hold the key to understanding how supermassive black holes grew so monstrously large, especially in the early universe. One leading theory suggests they formed from the direct collapse of massive primordial gas clouds, bypassing the stellar phase entirely. Others propose they grew through relentless mergers of smaller black holes in dense star clusters. But without actual observations, these ideas remain speculative. There are tantalizing clues, though. A handful of candidates have emerged, like HLX-1 in a distant galaxy, which appears to be around 20,000 solar masses, potentially the first confirmed intermediate mass black hole. Then there's the bizarre object in the globular cluster Omega Centauri, where stars orbit an unseen mass equivalent to 50,000 suns. These outliers hint that intermediate black holes might exist but are exceptionally rare or hidden in plain sight. The challenge is detection. Unlike their supermassive cousins, intermediate black holes don't have vast accretion disks emitting bright radiation. And unlike stellar black holes, they're often too distant for us to spot their gravitational influence on nearby stars. Gravitational wave astronomy might change this. Collisions involving intermediate mass black holes would produce distinct ripples in spacetime. In fact, the LIGO Observatory detected a suspicious merger in 2019 that created a black hole of 142 solar masses, possibly our first indirect evidence. Some scientists argue we're looking in the wrong places. Dwarf galaxies, the small, ancient building blocks of larger galaxies, might harbor these missing links, having preserved them from early cosmic epochs. Others suggest they're lurking invisibly in the voids between galaxies, having been ejected during violent galactic mergers. The missing link problem forces us to reconsider black hole formation theories. Perhaps intermediate mass black holes were once common but got swallowed by growing supermassive ones, leaving few survivors. Maybe they form under such specific conditions that they're cosmic rarities. Whatever the answer, solving this mystery will rewrite our understanding of how the universe builds its most extreme objects. For now, these ghostly middleweights remain one of astronomy's great unsolved cases, hidden players in the black hole family tree, waiting to be found. Now, let's turn our attention to a fascinating cosmic paradox: why some supermassive black holes feast like kings while others endure cosmic famines. Picture the universe's most powerful objects on radically different diets, and you'll begin to unravel one of the great mysteries of galactic evolution. At the heart of nearly every galaxy sits a supermassive black hole, but their eating habits couldn't be more diverse. Some, like the one in our own Milky Way, are relatively quiet, nibbling on the occasional passing star or gas cloud. Others, particularly in active galactic nuclei, devour enormous amounts of material, glowing brilliantly as quasars, the brightest objects in the universe. So what determines whether a black hole sits on a starvation diet or indulges in a cosmic buffet? The answer lies in their galactic environment. A black hole's feeding frenzy depends largely on how much gas and stars are funneled toward its event horizon. In spiral galaxies like ours, where gas is spread thinly and orbits are stable, the central black hole often goes hungry. But in galaxies undergoing mergers or intense star formation, chaos reigns, gas clouds collide, spiral inward, and trigger feeding episodes that can last millions of years. There's also the question of timing. Many supermassive black holes experience cycles of activity, swinging between periods of gluttony and prolonged fasting. These cycles might be tied to the availability of fuel. Once a black hole consumes nearby material, it may have to wait for fresh reserves to be delivered by galactic processes. Some researchers even speculate that black holes burp after large meals, releasing powerful jets that clear out surrounding gas and temporarily shut off their own food supply. But the consequences of these dietary extremes go far beyond the black holes themselves. They shape the fate of entire galaxies. When a supermassive black hole feasts, the energy released can heat up surrounding gas, preventing it from cooling and forming new stars. This process, called quenching, may explain why some galaxies transition from vibrant, star-forming spirals into red and dead ellipticals. Meanwhile, galaxies with starving black holes may continue forming stars undisturbed for billions of years. Intriguingly, the most massive black holes seem to regulate their own diets through feedback mechanisms. As they consume matter, the resulting radiation and jets can blow away nearby gas, effectively putting themselves on a diet. This cosmic self-control might explain why we don't see black holes growing infinitely large. They eventually reach a point where they push their food away faster than they can swallow it. The starving giants raise another puzzle. If supermassive black holes need constant feeding to grow, how did the earliest ones, already billions of solar masses when the universe was less than 1 billion years old, get so big so fast? Some theories suggest they bypassed normal growth by feasting on enormous reservoirs of cold gas in the early universe. Others propose they grew through rapid mergers in crowded galactic nurseries. By studying these extreme eating habits, astronomers are piecing together how black holes and their host galaxies evolve together, an intricate cosmic dance where appetite shapes destiny. Whether starving or feasting, these celestial behemoths leave an indelible mark on the universe around them. Now, let's venture into one of the most mind-bending effects of supermassive black holes, their ability to warp time itself. Imagine standing near the edge of a black hole's event horizon, watching as the universe around you speeds up while your own clock seems to crawl. This isn't science fiction. It's the real, observable consequence of Einstein's theory of general relativity. The closer you get to a supermassive black hole, the more extreme its gravitational pull becomes. This doesn't just bend space, it stretches time in ways that defy our everyday experience. Picture this: if you could hover near the event horizon without being torn apart, of course, your watch would tick far slower than a clock back on Earth. To someone observing you from a safe distance, your movements would appear to slow down, almost as if you were moving through thick molasses. In fact, at the very edge of the event horizon, time would seem to stop entirely from their perspective. You'd freeze in place, never quite crossing over, while the outside universe races ahead without you. This phenomenon, called gravitational time dilation, has been tested right here in our own solar system. Satellites in Earth's orbit, where gravity is slightly weaker, run a tiny bit faster than clocks on the ground. But near a supermassive black hole, the effect is millions of times more dramatic. If you could spend just 1 hour close to its event horizon and then return home, you might find that centuries or even millennia had passed on Earth. It's the ultimate cosmic time machine, except there's no going back. What makes this even wilder is that the black hole doesn't just slow time, it twists light in bizarre ways too. If you were looking outward from near the event horizon, the entire universe would appear compressed into a bright ring above you, warped by the black hole's gravity. Stars behind it wouldn't just be hidden, they'd be duplicated, their light bent around the black hole to create multiple ghostly images. Even your own light would struggle to escape, red shifted into invisibility as it fights against the gravitational pull. This time-warping effect isn't just a curiosity, it has real consequences for how we observe black holes. When matter spirals into one, the light it emits gets stretched and slowed, creating the eerie, slow-motion glow we detect with telescopes. It's why the gas swirling around supermassive black holes appears to move at a crawl, even as it's actually screaming inward at nearly the speed of light. And here's the kicker: because time near a black hole runs so much slower, the universe outside evolves at what seems like breakneck speed. A black hole that's billions of years old from our perspective might have experienced only a brief moment of existence from its own point of view. It's a cosmic hall of mirrors where time itself becomes fluid, challenging everything we think we know about reality. So the next time you glance at a clock, remember, it's not just ticking away seconds. It's measuring a moment in the vast, elastic fabric of space-time, a fabric that supermassive black holes twist into knots. And somewhere out there, near one of these gravitational monsters, time is flowing at an entirely different pace, reminding us just how strange and wondrous the universe truly is. Now, let's shift our focus to something equally fascinating: the surprising influence supermassive black holes have over their entire galaxies. Far from being passive cosmic vacuum cleaners, these invisible giants act like galactic conductors, orchestrating the birth and death of stars across unimaginable distances. At first glance, it might seem impossible for a black hole, a single point in space, to control something as vast as an entire galaxy. But the key lies in the tremendous energy they release as they devour matter. When gas and dust spiral into a supermassive black hole, they don't just vanish quietly. Instead, they heat up to millions of degrees, creating colossal outbursts of radiation and powerful jets of charged particles. These outbursts can blow outward with such force that they sweep away entire clouds of star-forming gas, effectively putting the brakes on new star birth. Picture a galaxy where stars should be forming at a furious pace, with vast reserves of gas ready to collapse into new suns. But then, the central black hole awakens, sending out shockwaves of energy that push that gas away like a cosmic hurricane. Suddenly, the stellar nurseries are emptied and the galaxy's star-making factories shut down. Astronomers call this quenching, and it's one of the most dramatic ways black holes shape their cosmic neighborhoods. But it's not all about destruction. In some cases, the same forces that quench star formation in one region can actually trigger it in another. When those high-speed jets slam into distant gas clouds, the shockwaves can compress the material just enough to spark new stars. It's a delicate balance, like a cosmic gardener who prunes some branches while encouraging others to grow. We've even seen this play out in our own cosmic backyard. Take the galaxy Messier 87, home to the first black hole ever imaged by the Event Horizon Telescope. Its jets stretch for thousands of light years, and researchers have spotted pockets of star formation along their edges, likely ignited by the very forces that suppress star birth closer to the core. The most astonishing part, this interplay between black holes and galaxies might explain why we don't see nearly as many massive galaxies as theories predict. Without black holes putting limits on star formation, the universe could be packed with overly bloated galaxies. Instead, these gravitational titans act as cosmic regulators, maintaining a balance that shapes the large-scale structure of the universe itself. So the next time you gaze at a spiral or elliptical galaxy, remember, its beauty isn't just the work of gravity and time. Hidden in its heart, a supermassive black hole is pulling invisible strings, conducting a symphony of creation and destruction that spans billions of years. And in that dance, we find one of the universe's most profound secrets, the invisible hand that guides the life cycle of galaxies. Now, let's unravel another cosmic mystery. What happens when not one, but two supermassive black holes share the same galactic neighborhood? It turns out some galaxies are home to binary black holes, a rare and chaotic duo locked in a gravitational dance, often the result of ancient galactic collisions. Picture two galaxies, each with its own supermassive black hole at the center, drifting toward each other over billions of years. When they finally merge, their black holes don't just vanish, they spiral closer and closer, eventually forming a binary system. These pairs can orbit each other for millions or even billions of years, sometimes stalling just light years apart, unable to merge due to a phenomenon called the final parsec problem. Without enough nearby stars or gas to steal their orbital energy, they remain in a near-endless cosmic standoff. But when they do finally collide, the universe shakes. The merger of two supermassive black holes unleashes the most powerful gravitational waves in existence, ripples in spacetime itself. These waves carry more energy than all the stars in the observable universe combined, yet they're so faint by the time they reach us that detecting them requires instruments like LIGO and the future LISA Space Observatory. The discovery of such waves would confirm one of Einstein's boldest predictions and open a new window into understanding black hole growth. Some of the best evidence for these binary systems comes from galaxies with wobbling jets. Take the galaxy OJ 287, where astronomers have observed erratic bursts of light every 12 years, likely caused by a smaller black hole plunging through the accretion disk of its larger companion. Another telltale sign, quasars with double sets of spectral lines, hinting at two separate black holes orbiting each other. What's even more mind-bending is that some galaxies might host 3 or more supermassive black holes, a scenario possible in dense galaxy clusters where multiple mergers occur. Simulations suggest these chaotic systems can fling one black hole outward at incredible speeds while the others merge, creating rogue black holes hurtling through intergalactic space. So why does this matter? Binary black holes aren't just cosmic oddities, they're fossil records of galactic evolution. By studying them, we piece together how galaxies grow through collisions, and one day we might even hear their mergers through gravitational waves, uncovering secrets about the universe's most violent encounters. The next time you look up at the night sky, remember, some galaxies out there aren't just ruled by one invisible titan, they're governed by two. Now, let's tackle one of the most puzzling questions in modern physics. What happens to information that falls into a black hole? This isn't just about stars or gas disappearing into the void. It's about whether the universe itself forgets. Stephen Hawking's famous information paradox challenges everything we thought we knew about how black holes behave, and the implications are enough to make even the most seasoned physicists pause. Here's the heart of the problem. According to quantum mechanics, information, the fundamental details that describe every particle in the universe, can never be destroyed. It might change form, but it's always preserved like a cosmic ledger keeping track of every event. But black holes, as described by Einstein's general relativity, are the ultimate shredders. Anything that crosses the event horizon is gone forever, crushed into the singularity. So, what happens to that information? Does it vanish, violating quantum law, or does it somehow survive? Hawking initially argued that black holes don't just swallow matter, they erase information entirely. As a black hole emits Hawking radiation, slowly evaporating over unimaginable timescales, the radiation appears random, carrying no trace of what fell in. That would mean the universe's ledger has missing pages, a notion that horrified physicists. If information can disappear, the foundation of quantum theory crumbles. This became known as the information paradox, a clash between two pillars of physics. But modern research suggests a resolution might lie in the black hole's event horizon itself. Imagine the horizon not as a one-way door to oblivion, but as a scrambled mirror. The holographic principle proposes that all the information about what falls into a black hole gets encoded on its surface, like a two-dimensional hologram storing a three-dimensional reality. As the black hole evaporates, that information could gradually leak back out through Hawking radiation, just in an incredibly scrambled form. It's like burning a book. The words seem lost in the ashes, but with enough effort, you could theoretically reconstruct them. Some physicists take this even further. The firewall hypothesis suggests the event horizon might be a raging inferno of high-energy particles, destroying anything that touches it while preserving information in the radiation. Others argue for quantum hair, subtle imprints on a black hole's exterior that record what fell in. While the debate isn't settled, one thing's clear: solving this paradox could revolutionize our understanding of space, time, and the very fabric of reality. Why does this matter beyond theoretical physics? If information isn't lost, it hints at a deeper order to the universe, a hidden symmetry governing even the most extreme environments. And if black holes can preserve information, they might be nature's ultimate time capsules, holding clues about the birth of galaxies, the nature of dark matter, or even the origin of the cosmos itself. The next time you hear about a black hole, remember, it's not just a cosmic vacuum. It's a puzzle waiting to be solved, one that might rewrite the laws of physics as we know them. Now, let's dive into one of the most tantalizing mysteries in cosmology: the possible connection between supermassive black holes and dark matter. It's a cosmic detective story that could rewrite our understanding of the universe's hidden architecture. Dark matter is the invisible glue holding galaxies together, making up roughly 85% of all matter in the cosmos. Yet, despite decades of searching, we still don't know what it's made of. Here's where supermassive black holes enter the picture. Some scientists propose that these gravitational giants might not just coexist with dark matter, they could be deeply intertwined with it. One bold theory suggests that dark matter itself might consist of ancient black holes, born in the chaos of the early universe. These hypothetical objects, called primordial black holes, wouldn't form from collapsing stars like ordinary black holes. Instead, they'd be relics of the Big Bang, forged when dense regions of the infant universe collapsed under their own gravity. If they exist, primordial black holes could solve two puzzles at once: the nature of dark matter and the origin of supermassive black holes. Imagine a scenario where countless tiny primordial black holes merged over billions of years, eventually growing into the monsters we see at galactic centers today. But the evidence is far from clear. Some astronomers point to gravitational lensing events, brief flashes of light caused by invisible objects bending space-time, as potential sightings of these dark matter candidates. Others argue that if primordial black holes were abundant, we'd see more direct signs like frequent ripples in space-time from their collisions. The debate is heated, with some researchers calling the idea a long shot, while others see it as a missing piece of the cosmic puzzle. There's another twist. Supermassive black holes might not just be products of dark matter, they could also shape its behavior. Simulations show that the gravitational pull of a central black hole can drag dark matter into dense spikes around it, altering how galaxies form and evolve. In some extreme cases, these dark matter halos might even feed the black hole, creating a feedback loop that fuels its growth. Why does this matter? If supermassive black holes and dark matter are linked, it could reveal fundamental truths about how structure emerges in the universe. It might explain why galaxies without visible black holes, so-called dark galaxies, defy our expectations, or why some supermassive black holes appeared so early in cosmic history when there wasn't enough time for them to grow by conventional means. The search continues, with next-generation telescopes and gravitational wave detectors poised to test these ideas. Whether or not primordial black holes prove to be the dark matter we've been hunting, the very possibility reminds us of something profound. The universe's greatest mysteries are often hidden in plain sight, waiting for us to connect the dots. Now, let's take a daring leap into one of the most mind-bending ideas in theoretical physics: the possibility that supermassive black holes might not be cosmic dead ends, but gateways to something even stranger: white holes. If black holes are the universe's ultimate vacuum cleaners, sucking everything in, white holes would be their polar opposites, cosmic fountains, spewing out matter and energy relentlessly. And here's the wildest part: some theories suggest these two extremes could be connected through wormholes, like a tunnel through space-time itself. The concept of white holes emerges from the same equations that predict black holes. In Einstein's theory of general relativity, the math allows for solutions where time runs backward, effectively turning a black hole inside out. Instead of an event horizon that traps everything, a white hole would have an event horizon that repels everything, ejecting matter so violently that nothing could ever enter. Picture a black hole in reverse, blasting out light, gas, and even entire stars at speeds approaching light itself. But why would nature create such bizarre objects? One compelling idea is that white holes could be the other end of black holes, connected by a wormhole, a theoretical shortcut through the fabric of space and time. Imagine falling into a supermassive black hole at the center of a galaxy, only to emerge from a white hole in another galaxy, or even another universe entirely. It's the stuff of science fiction, but some physicists take it seriously as a mathematical possibility. There's just one problem: white holes violate the second law of thermodynamics, which says entropy, or disorder, always increases. A white hole would essentially be a cosmic reset button, ejecting pristine, low-entropy matter into the universe, which shouldn't happen naturally. That's why most scientists think white holes, if they exist at all, would be incredibly rare or short-lived. Some theories suggest they might only appear in the very early universe or as the final burst of a dying black hole via quantum effects. Yet there are tantalizing clues that keep the idea alive. Some astronomers have spotted bizarre, one-off explosions in deep space, brief, intense bursts of energy with no obvious source. Could these be white holes flaring into existence before vanishing again? Others speculate that the Big Bang itself might have been a white hole event, with our universe erupting from a singularity in some higher dimensional space. The most exciting possibility, though, is that wormholes linking black and white holes could enable interstellar travel, or even time travel. If you could survive the journey through a supermassive black hole's crushing gravity and chaotic interior, you might theoretically emerge somewhere or someone else entirely. Of course, the physics is far from settled. Wormholes would require exotic matter with negative energy to stay open, and no one knows if such matter even exists. So where does this leave us? White holes remain one of the most speculative ideas in cosmology, but they force us to ask profound questions. Could the universe recycle itself through black and white holes? Is our reality just one side of a cosmic coin with another universe on the reverse? For now, these mysteries linger at the edge of known physics, waiting for the next breakthrough to either confirm them or consign them to the realm of beautiful but impossible dreams. One thing's certain: if white holes are real, they'd rewrite the rules of existence itself. Now, let's peel back another layer of cosmic mystery, one that challenges our very understanding of reality itself. What if everything we think we know about black holes is just the surface of something far deeper? Buckle up, because we're diving into a theory so radical it suggests the universe might be a hologram, and supermassive black holes could be holding the key. Here's the mind-blowing idea. The holographic principle proposes that all the information contained within a volume of space, like the unfathomable complexity inside a black hole, can actually be encoded on its two-dimensional surface like a cosmic hard drive. Think of it this way: imagine watching a 3D movie on a flat screen. Even though the image appears three-dimensional, all the data is stored on a 2D surface. Now apply that to a black hole. The mind-bending implication: the three-dimensional space inside might just be a projection of information stored on its event horizon. This isn't science fiction, it's a serious theory born from trying to solve the infamous black hole information paradox. When matter falls into a black hole, it seemingly vanishes, violating quantum mechanics' rule that information can't be destroyed. But if the holographic principle is correct, that information isn't lost, it's imprinted on the black hole's surface in tiny, Planck-scale pixels. Every particle, every bit of energy that crosses the event horizon could leave a footprint there, like data etched onto a disk. Supermassive black holes are the ultimate test for this idea. Their enormous event horizons act like vast cosmic canvases, potentially storing staggering amounts of information. Some calculations suggest a single supermassive black hole could hold more information than all the books ever written, all the movies ever made, compressed into a layer no thicker than a single atom. And here's where it gets even stranger. If this is true for black holes, could the entire universe work the same way? Might our 3D reality just be a projection from some distant two-dimensional boundary? The math behind this is fiendishly complex, but the implications are staggering. If black holes are holograms, they might be showing us that space, time, and even gravity aren't fundamental. They're emergent phenomena, like the surface of a lake emerging from countless water molecules. This could be the clue that finally unites quantum mechanics and general relativity, two theories that have stubbornly refused to fit together for a century. Of course, not everyone's convinced. Critics argue that without direct evidence, the holographic principle remains speculative, but tantalizing hints are emerging. Some physicists have found that the equations governing quantum entanglement, the spooky action at a distance that links particles across space, behave eerily like holographic projections. Others point to the way black holes seem to maximize entropy at their surfaces, as if optimizing data storage. So where does this leave us? If supermassive black holes really are cosmic hard drives, they're not just monsters lurking in galactic centers. They're the universe's ultimate archivists, preserving every scrap of information that falls into them. And if the holographic principle holds, they might be showing us that reality itself is far stranger, far more interconnected than we ever imagined. One thing's certain: unlocking this secret wouldn't just rewrite astrophysics textbooks, it'd redefine what it means to exist. Now, let's shift our gaze from the mind-bending holographic universe to something equally astonishing: stars racing across the cosmos at unimaginable speeds. Picture a cosmic pinball machine where supermassive black holes act as the ultimate flippers, launching stars so fast they defy gravity's grip. These aren't just fast stars, they're hypervelocity stars, some flying so rapidly they're flung entirely out of their home galaxies. How does this happen? It all comes down to a gravitational dance with a supermassive black hole. Imagine a binary star system, two stars orbiting each other, wandering too close to the monster at the galactic center. The black hole's immense gravity can tear the pair apart, capturing one star while slingshotting the other away at speeds exceeding 1 million miles per hour. It's like a cosmic version of a slingshot maneuver spacecraft use around planets, but on a scale so violent it can eject stars into the void between galaxies. The first hypervelocity star was discovered in 2005, racing away from the Milky Way at nearly twice the speed needed to escape our galaxy's gravity. Since then, astronomers have spotted dozens more, some with velocities so extreme they'll never return. These stars aren't just cosmic oddities, they're messengers. By tracing their paths backward, scientists can map the hidden dynamics of supermassive black holes, revealing details about their mass and even the shape of their gravitational fields. Some of these ejected stars are massive blue giants, burning bright and hot, while others are smaller, like our Sun. But speed isn't their only surprising trait. A few hypervelocity stars are even racing toward us, hurled from other galaxies by their own supermassive black holes. Imagine a star born in Andromeda, flung across millions of light years, only to streak through our galactic neighborhood. What's truly breathtaking is the sheer energy involved. The acceleration these stars experience in just seconds would vaporize any known material. Yet they survive, carrying clues about the most extreme environments in the universe. Some may even harbor planets, though any orbiting worlds would have been torn away or reduced to scorched rubble during ejection. This phenomenon isn't just a spectacle, it's reshaping our understanding of galaxy evolution. As supermassive black holes fling stars into intergalactic space, they're effectively seeding the cosmos with rogue stellar travelers. Some theorists suggest these homeless stars could even collide with other galaxies, delivering fresh material far from their origins. So the next time you look up at the night sky, remember, somewhere out there, stars are fleeing their homes at unimaginable speeds, all thanks to the slingshot power of supermassive black holes. And if one of these cosmic outcasts ever heads our way, it'll be a fleeting but spectacular reminder of the violent beauty lurking at the heart of every galaxy. Now let's zoom out from individual stars and galaxies to see the universe's grand design, where supermassive black holes act as cosmic anchors in the vast web of spacetime. Picture the universe not as a random scatter of galaxies, but as an intricate network of filaments, like a colossal spiderweb stretching across billions of light years. At the intersections of these filaments, where the threads knot together, you'll often find supermassive black holes lurking at the heart of galaxy clusters like invisible puppeteers. These black holes aren't just passive occupants, they're active architects shaping the cosmos on the largest scales. Scientists call this structure the cosmic web, and it's made of dark matter and gas, with galaxies strung along its strands like pearls on a necklace. But the heaviest pearls, those dense galaxy clusters, almost always contain supermassive black holes at their cores. Their gravity doesn't just influence their immediate surroundings, it sends ripples through the entire web. Here's how it works. When galaxies collide and merge, their central black holes eventually spiral together, creating even more massive black holes. These mergers release tremendous energy, heating the surrounding gas and preventing it from cooling to form new stars. This means the black hole indirectly controls how many stars its host cluster can produce. In some cases, the energy output is so extreme it carves out bubbles in the hot gas between galaxies, leaving voids that can span millions of light years. But the influence goes even deeper. The cosmic web's filaments funnel gas toward these dense nodes, feeding both the galaxies and their central black holes. It's a self-reinforcing cycle. The black hole grows as it feeds, and its outbursts regulate the flow of gas along the web. Some researchers believe this process might explain why we see galaxy clusters where we do, with supermassive black holes acting as gravitational signposts marking the web's densest intersections. One of the most striking examples is the Perseus cluster, home to one of the most massive black holes known. Observations show vast sound waves, yes, actual sound waves in space, rippling through the cluster's gas created by the black hole's periodic outburst. These waves carry energy across the cluster, helping to maintain its structure. Without them, the gas might cool too quickly, triggering runaway star formation and drastically altering the cluster's evolution. What's truly mind-blowing is the timescale. The cosmic web has been forming for over 13 billion years, and supermassive black holes have been shaping it for nearly as long. Some of the earliest quasars, bright beacons powered by young, ravenous black holes, already sat at web nodes when the universe was less than 1 billion years old. Their rapid growth suggests they were born into dense environments where the cosmic web's filaments fed them efficiently. So the next time you hear about the large-scale structure of the universe, remember supermassive black holes aren't just lurking in galaxies. They're woven into the fabric of the cosmos itself, anchoring the universe's grand design. And as we map more of the cosmic web, their role as master builders of the universe becomes ever clearer. Now, let's turn our attention to one of the most powerful yet invisible forces at work around supermassive black holes, their monstrous magnetic fields. These cosmic powerhouses don't just dominate through gravity alone. They generate magnetic fields so intense they can twist space-time itself, shaping the violent chaos of their surroundings in ways that defy imagination. Picture the accretion disk, a swirling maelstrom of superheated gas and plasma orbiting the black hole at nearly light speed. As these particles collide and churn, they create electric currents, which in turn generate magnetic fields. But here's where things get extreme. The black hole's rotation, combined with the sheer energy of the inflowing matter, amplifies these fields to strengths billions of times more powerful than Earth's magnetic field. These magnetic fields don't just sit idle, they become active players in the black hole's feeding frenzy. They twist into towering, helical structures that rise above the accretion disk like cosmic tornadoes. Some of this magnetic energy gets funneled into those spectacular relativistic jets we've seen shooting out from black holes at nearly the speed of light. Without these magnetic fields, those jets wouldn't exist. The fields act like particle accelerators, channeling and collimating the jets into narrow beams that can stretch across thousands of light years. But the influence goes even deeper. These magnetic monsters also regulate how the black hole feeds. In some cases, the fields grow so strong they actually push back against the infalling gas, creating a balancing act between gravity's pull and magnetic pressure. This can lead to dramatic outbursts like cosmic hiccups where the black hole temporarily stops feeding, only to restart once the fields relax. One of the best examples lies in the heart of Galaxy M87, home to the famous black hole captured by the Event Horizon Telescope. Observations reveal intricate magnetic field lines woven through its accretion disk, helping to launch its massive jet. Scientists believe these fields might even explain why some black holes have jets while others don't. The orientation and strength of the magnetic fields could be the deciding factor. What's truly fascinating is how these magnetic fields might solve one of astrophysics' biggest puzzles: how black holes manage to convert so much of their infalling mass into energy. While only a fraction of the gas actually crosses the event horizon, the magnetic fields extract energy from the black hole's spin, supercharging particles and flinging them outward. This process can be up to 10 times more efficient than nuclear fusion, turning the black hole into the ultimate cosmic power plant. So the next time you marvel at the image of a black hole's shadow or the brilliance of its jets, remember, it's not just gravity at work. These invisible magnetic monsters are the unseen architects, shaping the destiny of everything that dares to venture too close. And as we peer deeper into their mysteries, we're uncovering the fundamental forces that govern the most extreme environments in the universe. Now, let's take a closer look at one of the most iconic images in modern astronomy, the black hole's shadow. You might remember the groundbreaking photo of the supermassive black hole at the center of galaxy M87, released by the Event Horizon telescope. That dark silhouette, encircled by a fiery golden ring, isn't just a stunning visual, it's packed with secrets about the nature of spacetime itself. That shadow isn't the event horizon, as some might assume. Instead, it's something even more fascinating, a region where light bends so dramatically around the black hole that it creates what scientists call a photon ring. Picture this: photons, or particles of light, orbit the black hole in a last dance before either escaping to our telescopes or vanishing forever into the abyss. The shadow is essentially the absence of light that gets too close and can't escape, while the bright ring is the warped glow of superheated gas swirling around the black hole, its light magnified by the black hole's immense gravity. What makes this shadow so special is its shape. Einstein's theory of general relativity predicted that a spinning black hole would distort spacetime so much that its shadow should appear slightly squashed like a wobbly circle. And sure enough, when scientists analyzed the image, the shadow matched those predictions almost perfectly. This wasn't just a victory for Einstein, it was proof that we're peering directly into the heart of spacetime's most extreme warping. But here's where it gets even wilder. That glowing ring isn't uniform, it's brighter on one side. Why? Because the black hole's rotation drags spacetime around with it, like a whirlpool twisting the light from the accretion disk. The side where the gas is moving toward us appears brighter due to a phenomenon called relativistic beaming, where light gets boosted to higher energies. Meanwhile, the side moving away dims. This asymmetry isn't just cosmetic. It tells us exactly how fast the black hole is spinning and even the angle at which we're viewing it from Earth. The size of the shadow is another goldmine of information. Since a black hole's shadow scales with its mass, measuring its diameter lets astronomers calculate the black hole's weight with incredible precision. For M87's black hole, that shadow spans about 40 billion kilometers, 3 times wider than our entire solar system. And yet, despite its colossal size, capturing it required a telescope as big as Earth itself, made possible by linking observatories across the globe. But the real mind-bender, that shadow isn't static. If we could watch it over time, we'd see it flicker and pulse as hotspots in the accretion disk orbit the black hole, creating tiny flashes in the ring. Future observations might even reveal how the shadow changes as the black hole devours more matter or interacts with nearby objects. So the next time you see that haunting image of the black hole's shadow, remember, you're not just looking at a cosmic monster. You're seeing the ultimate laboratory for testing the laws of physics, where gravity twists light into impossible shapes and reveals secrets about the universe we couldn't uncover any other way. And as our telescopes grow sharper, these shadows will keep whispering their mysteries, helping us decode the deepest truths of spacetime. But here's something that might surprise you: black holes, for all their terrifying complexity, are actually incredibly simple at their core. Think about it like this: no matter what falls into a black hole, whether it's a star, a planet, or an entire spaceship, the black hole itself only remembers 3 things about it. This idea is called the no-hair theorem, and it's one of the strangest and most elegant principles in physics. The name might sound funny, but it's actually a metaphor. Just like a bald head has no hair to distinguish it, a black hole has no extra features beyond its mass, spin, and electric charge. Everything else, every detail about the objects it swallows, gets erased forever. Imagine throwing a grand piano, a library of books, and a vintage car into a black hole. After they cross the event horizon, the black hole doesn't remember the piano's shape, the words in the books, or the car's color. All that information gets scrambled into oblivion, leaving behind only 3 numbers: how heavy the black hole is, how fast it's spinning, and whether it's positively or negatively charged. That's it. Now you might wonder, how can something so destructive be so simple? The answer lies in gravity's extreme power. Inside a black hole, gravity crushes matter beyond recognition, stripping away all its unique properties until only these 3 universal traits remain. It's like the ultimate cosmic erase button, but here's where it gets even weirder. The no-hair theorem suggests that if you had 2 black holes with identical mass, spin, and charge, you wouldn't be able to tell them apart, even if one formed from collapsed stars and the other from an entire galaxy's worth of gas. To an outside observer, they'd be perfect twins. This simplicity is both a blessing and a puzzle for physicists. On one hand, it means black holes are easier to study than we might expect, since they're defined by just 3 numbers. Scientists can model their behavior with remarkable precision. On the other hand, it creates a massive problem. What happens to all that lost information? According to quantum mechanics, information can't be destroyed, so where does it go when a black hole swallows it? This contradiction is at the heart of one of physics' biggest debates, and it's why the no-hair theorem isn't just a quirky idea. It's a gateway to some of the deepest mysteries in the universe. Some theories suggest the information might be encoded on the black hole's event horizon, like a cosmic hard drive. Others propose it leaks back out through Hawking radiation over trillions of years. So while the no-hair theorem makes black holes seem simple, it's actually pointing us toward a far more complicated truth, one that might force us to rewrite the laws of physics as we know them. And that's what makes these cosmic giants so endlessly fascinating. They're not just destroyers. They're the ultimate teachers, showing us where our understanding of reality starts to unravel. Now let's venture into the quantum realm, where the fabric of space-time itself gets a little frothy. Picture this: right at the edge of a supermassive black hole's event horizon, where gravity bends reality to its will, something extraordinary happens. The smooth, predictable space-time we're used to dissolves into a chaotic dance of quantum fluctuations, a phenomenon physicists call quantum foam. Imagine stirring a cup of coffee until the surface erupts with tiny, fleeting bubbles. That's roughly how space-time behaves at microscopic scales near a black hole's edge. Except instead of bubbles, you get unpredictable, minuscule twists and ripples in the fabric of reality itself. These fluctuations are so violent that even concepts like here and there, or now and then, lose their meaning. Space and time cease to be smooth and continuous. Instead, they become a seething, probabilistic mess. So why does this matter? Because quantum foam might be our best clue to unlocking the holy grail of physics, a theory of quantum gravity. Right now, Einstein's general relativity explains the cosmos on large scales, while quantum mechanics rules the tiny world of particles. But where these 2 theories collide, like at the edge of a black hole, they break down completely. Quantum foam is where that battle plays out in real time. Here's the wild part: supermassive black holes act like cosmic laboratories, magnifying these quantum effects to scales we might actually detect. Their immense gravity stretches space-time so thin that the foaminess becomes visible to our instruments, or at least in theory. Some scientists believe that by studying the light or gravitational waves skimming a black hole's event horizon, we could spot telltale signs of this foamy structure. It would be like finding fingerprints of quantum gravity in the universe's most extreme environment. But there's a catch. Quantum foam operates at scales 1 billion trillion times smaller than an atom, making it nearly impossible to observe directly. That's where black holes give us an edge. Their extreme conditions amplify these tiny effects, like a microscope for space-time itself. If we can decode the subtle distortions in the light or waves escaping their grip, we might finally bridge the gap between gravity and quantum mechanics. What's at stake? Nothing less than our understanding of reality. If quantum foam exists as predicted, it would mean that space-time isn't the smooth, continuous stage we've always assumed, but rather a dynamic, ever-changing quantum landscape. And supermassive black holes, with their unmatched gravitational might, are the perfect places to test this radical idea. So next time you hear about a black hole's event horizon, remember, it's not just a point of no return. It's a window into the quantum chaos that underpins the universe, a place where space-time itself boils with secrets waiting to be uncovered. Now, let's shift our gaze to one of the most puzzling cosmic riddles: dark energy. While supermassive black holes warp space with their gravity, dark energy does the opposite, stretching the universe apart at an ever-increasing rate. At first glance, these forces seem unrelated, one crushing, the other expanding, but recent discoveries hint at a connection so strange it could rewrite our cosmic rulebook. Picture the universe like an inflating balloon. Dark energy is the breath filling it, while supermassive black holes are knots tied into its rubber surface. For decades, scientists assumed these knots simply rode along with the expansion. But new data suggests something far more intriguing. The growth of these black holes might actually be fueling the acceleration itself. Here's how this counterintuitive idea works. As supermassive black holes feast on gas and stars, they release colossal amounts of energy into their surroundings, not just as light, but as gravitational waves and high-speed jets. Some theories propose that this energy output subtly alters the fabric of space-time on cosmological scales, effectively mimicking the effects of dark energy. Imagine tossing pebbles into a pond. Each ripple is small, but trillions of ripples could shift the water's entire surface. The numbers are staggering. A study published in the Astrophysical Journal calculated that if just a fraction of the energy from black hole mergers and accretion disks were converted into dark energy-like effects, it could account for the observed acceleration of the universe. Even more startling, the timing matches. The universe's expansion began speeding up around 5 billion years ago, coinciding with peak supermassive black hole activity across cosmic history. But here's where things get truly mind-bending. If black holes are linked to dark energy, their growth might not follow the rules we thought. Traditional models assume these giants swell by swallowing matter, but alternative ideas suggest they could gain mass from the universe's expansion itself, a process called cosmological coupling. Think of it like a rubber band stretching. As space expands, the black holes embedded in it might absorb energy from that stretching, growing without eating. This isn't just theoretical. Astronomers have spotted supermassive black holes in modern galaxies that are up to 20% larger than expected based on ancient quasars from the early universe. One explanation: they've been feeding on the energy of cosmic expansion all this time. Of course, skeptics point out gaps in the theory. If black holes drive acceleration, why don't dwarf galaxies, which lack supermassive black holes, expand differently? Others argue we're seeing correlation, not causation. But the tantalizing possibility remains. What if the universe isn't just expanding because of dark energy, but because the darkest objects in it are actively participating in the process? Future telescopes like ESA's Euclid or Nancy Grace Roman could settle the debate by mapping millions of black holes across cosmic time. If their growth rates align with expansion metrics, we might be staring at the universe's ultimate recycling program, where black holes don't just shape galaxies but the very space between them. So the next time you hear about dark energy, remember, the answer to this cosmic mystery might not lie in empty space, but in the voracious hearts of supermassive black holes, quietly shaping the fate of everything around them. Now let's turn our attention to a concept so audacious, it sounds like science fiction: the black hole bomb. Imagine harnessing the raw power of a spinning supermassive black hole, not just observing its fury, but channeling it as the ultimate cosmic energy source. This isn't a fantasy, it's a serious theoretical possibility rooted in Einstein's equations, and it revolves around a phenomenon called superradiance. Here's how it works when a spinning black hole drags spacetime around it, an effect known as frame dragging. It can amplify certain waves of energy that pass near it. Think of it like a whirlpool in water. If you send ripples toward it at just the right angle and frequency, the whirlpool's rotation can make those ripples stronger as they scatter away. In the case of a black hole, this amplified energy could, in theory, be captured and harvested. The key lies in something called the ergosphere, a region just outside the event horizon where spacetime itself is twisted into a vortex by the black hole's spin. Any particle or wave entering this zone gets a boost of energy from the black hole's rotation. If you could reflect those amplified waves back toward the black hole, say, with a hypothetical mirrored shell surrounding it, they'd bounce back and forth, growing exponentially stronger with each pass. This creates a runaway feedback loop, like a microphone screech in an auditorium, but on a cosmic scale. The result, a bomb of concentrated energy that could, in theory, be extracted. The numbers are staggering. A typical supermassive black hole spinning at near light speed could release up to 40% of its mass as usable energy through superradiance. Compare that to nuclear fusion, our most efficient energy source on Earth, which converts less than 1% of mass into energy. That's the difference between lighting a match and detonating a supernova. But before we draft blueprints for black hole power plants, there's a catch. This process requires perfect conditions, an isolated, rapidly spinning black hole, and technology far beyond our current capabilities. Even so, the physics checks out. In fact, nature might already have its own version of this phenomenon. Some astrophysicists speculate that fast-spinning black holes in distant galaxies could be leaking energy via superradiance, potentially explaining certain mysterious bursts of radiation we've detected. The implications are mind-bending. If a civilization could master this technique, they'd unlock nearly unlimited energy, possibly even reaching Kardashev Type 3 status, controlling the power output of an entire galaxy. Of course, we're talking timelines spanning millennia, not years, but the mere possibility reshapes how we view black holes, not just as destroyers, but as potential engines of cosmic evolution. So while we're centuries away from building a black hole bomb, the math tells us it's not impossible, just unimaginably advanced, and that's the beauty of theoretical physics. It doesn't just reveal how the universe works, it shows us what the universe might allow if only we're clever enough to see it. Now let's shift our gaze to a true heavyweight champion of the cosmos, TON 618, the largest known black hole in the observable universe. This isn't just a supermassive black hole, it's an ultra-massive behemoth tipping the scales at a staggering 66 billion times the mass of our Sun. To put that into perspective, if our solar system were a marble, TON 618 would be the size of a small city. Picture this, the Schwarzschild radius of TON 618. The point of no return around its event horizon stretches over 1,300 astronomical units. That means if you replaced our Sun with this black hole, its event horizon would extend well beyond the orbits of all the planets, past the Kuiper belt, and even beyond the hypothetical Oort cloud, swallowing everything up to a distance 2,000 times farther than Pluto. What makes TON 618 even more astonishing is its appetite. This black hole powers a quasar so bright it outshines entire galaxies. The energy it emits as it devours surrounding matter is equivalent to trillions of suns. Yet, despite its monstrous size, TON 618 isn't some chaotic destroyer. It's a precision cosmic engine with an accretion disk so vast and hot that it generates light across the entire electromagnetic spectrum, from radio waves to deadly gamma rays. But here's the real kicker. TON 618 isn't just big, it's ancient. The light we see from it today started its journey when the universe was barely a tenth of its current age. That means this black hole somehow grew to its colossal size incredibly fast, defying our current models of black hole formation. Some theories suggest it could be the result of multiple galactic collisions, each funneling more material into its grasp, while others speculate it might have formed from the direct collapse of an impossibly massive primordial gas cloud. And yet, for all its grandeur, TON 618 raises more questions than answers. How does something this massive stabilize without tearing its host galaxy apart? Why haven't we found more black holes of this scale? These mysteries make it not just a record holder, but a cosmic puzzle that could rewrite our understanding of how the universe structures itself. So while we marvel at the sheer scale of TON 618, remember, it's not just a black hole. It's a boundary pusher, a reminder that the universe always has bigger, stranger secrets waiting in the dark. Now let's step into the vibrant light show of a supermassive black hole's most dazzling feature, the accretion disk. Imagine a cosmic carousel of gas and dust spinning at nearly the speed of light, heated to millions of degrees by friction and gravity. But here's the magic. This isn't just a scorching maelstrom. It's a natural prism splitting light into a breathtaking rainbow of energies, from searing X-rays to rumbling radio waves. The secret lies in the disk's temperature gradient. As matter spirals inward, it heats up dramatically, like water boiling faster as it nears the center of a whirlpool. Closest to the event horizon, temperatures soar to billions of degrees, emitting high-energy X-rays and gamma rays, light so powerful it could pierce through lead. Move outward and the gas cools slightly, glowing in ultraviolet and visible light, the same way a heating element shifts from white-hot to orange. Further still, where temperatures drop to thousands of degrees, the disk radiates infrared like the warmth from a space heater. And in the disk's outermost, cooler regions still hot enough to vaporize planets, the energy dips into radio waves, creating a low-frequency hum detectable across galaxies. This multi-wavelength spectacle isn't just beautiful, it's a scientific goldmine. Astronomers use these light fingerprints to map a black hole's feeding habits. X-rays reveal violent flares near the event horizon, while radio waves trace the slower, swirling outskirts. Some black holes, like the famous M87, even have their disks imaged in different light bands, showing how the disk structure changes with distance. And occasionally, when a star is torn apart in a tidal disruption event, the sudden influx of fresh material creates a temporary super rainbow, flaring across the spectrum like a cosmic alarm bell. But the real surprise, the colors we can't see. Some accretion disks emit polarized light, twisting it like a corkscrew due to intense magnetic fields. Others produce reverberation echoes, where X-rays bounce off nearby gas clouds, creating delayed signals that help astronomers measure the disk's size. Even the disk's rainbow isn't static. It flickers and pulses as magnetic fields snap and reconnect, launching jets or triggering bursts of energy. So next time you picture a black hole, don't just think of darkness. See it as a celestial projector, painting the universe with light from every corner of the electromagnetic spectrum. It's a reminder that even in the most extreme corners of space, there's a riot of color, if you know how to look. Now let's tune into one of the universe's most extraordinary concerts, the Black Hole Symphony. While we've marveled at the dazzling light shows of accretion disks, there's another hidden layer to these cosmic maelstroms: sound. Not in the way we hear music on Earth, of course space is silent, but through vibrations that ripple through the disk, creating patterns astronomers can detect like notes in a song. These vibrations start with the chaotic dance of matter in the disk. As gas and dust spiral toward the event horizon, they don't move smoothly. Turbulence, magnetic fields, and the black hole's immense gravity create oscillations, rhythmic pulses that travel through the disk like waves on a drumhead. Some vibrations are slow, taking hours or days to complete a cycle, while others flicker rapidly like the high notes of a piano. Scientists call these quasi-periodic oscillations, or QPO, and they're the key to decoding the black hole's hidden rhythms. Here's where it gets fascinating. Just as a musician's instruments reveal their size and shape by the sounds they produce, these vibrations tell us about the black hole's mass, spin, and even the structure of its disk. For example, high-frequency QPOs often trace the innermost stable orbit, the point of no return where matter plunges into the black hole. Lower frequencies, meanwhile, map the outer disk's wobbles like the deep hum of a cello. By studying these patterns, astronomers can essentially listen to a black hole's heartbeat, uncovering secrets invisible to telescopes alone. Some black holes even seem to harmonize with their jets. In systems like JRS 1915+5, rapid X-ray flickers appear synchronized with plasma eruptions, as if the disk's vibrations conduct the jet's outburst like a cosmic orchestra. Other times, when a star is torn apart by tidal forces, the resulting flares produce chaotic crescendos of X-rays, a temporary symphony of destruction before the black hole swallows its meal. But the most profound revelation, these vibrations might help solve one of astrophysics' biggest mysteries: what happens just outside the event horizon. Some theorists suggest QPOs could be echoes of space-time itself vibrating, a phenomenon predicted by Einstein's equations but never directly observed. If true, it would mean black holes don't just play music, they're instruments in the fabric of reality. So while we'll never hear these sounds with our ears, the universe has given us another way to listen. Each vibration, each oscillation, is a note in a grand cosmic composition, one that's rewriting our understanding of gravity, space-time, and the wild physics ruling the darkest corners of the universe. But hold on, because here's something that might surprise you. Everything you've heard about spaghettification might not be entirely true. That iconic image of objects getting stretched into long, thin noodles as they fall into a black hole. It's not always what happens. Let's clear up the confusion. Spaghettification occurs because of tidal forces, the difference in gravity between your head and feet if you were falling feet first toward a black hole. Near smaller black holes, these forces are extreme. The gravity at your feet is so much stronger than at your head that you'd be stretched like taffy long before reaching the event horizon. But with supermassive black holes, things play out differently. Their event horizons are so large, often bigger than our entire solar system, that the tidal forces near them are surprisingly gentle. If you crossed the event horizon of a supermassive black hole, you might not even notice anything unusual at first. The difference in gravity between your head and toes would be minimal, meaning no dramatic stretching. You'd simply float past the point of no return intact, at least until later when the crushing forces deep inside finally take over. Here's why this matters. It changes how we imagine black holes in popular culture. Movies often show spaceships or astronauts getting spaghettified instantly, but that's really only true for stellar mass black holes, the smaller ones formed from collapsing stars. With supermassive black holes, you could theoretically cross the event horizon unharmed, at least temporarily. Of course, you'd still be doomed, just not in the cinematic way we're used to seeing. There's another twist. For medium-sized black holes, the spaghettification point might actually lie inside the event horizon. That means if you fell in, you wouldn't get stretched until after you were already trapped, making the whole process invisible to outside observers. So while spaghettification is real, it's not the universal rule we once thought. Supermassive black holes rewrite the script, proving once again that these cosmic giants love to defy expectations. And that's the real takeaway. Black holes aren't just one-size-fits-all monsters. Their behavior depends entirely on their scale, and that's what makes them endlessly fascinating. Now let's turn to one of the most heated debates in modern physics, the black hole firewall paradox. Imagine approaching a black hole's event horizon, expecting to cross it smoothly, only to hit a blazing wall of energy that incinerates you instantly. That's the shocking proposal behind the firewall theory, and it's turned our understanding of black holes upside down. Here's why this idea exists. According to quantum mechanics, empty space isn't truly empty. Particle-antiparticle pairs constantly pop in and out of existence near the event horizon. Normally, one falls in while the other escapes as Hawking radiation. But this creates a problem. If the escaping particle carries information, the infalling particle must too, meaning the event horizon can't be the smooth, uneventful boundary Einstein's relativity predicts. Instead, it might be a searing layer of high-energy particles, a literal firewall. This clashes with relativity's no-drama principle, which states that someone crossing the event horizon shouldn't notice anything unusual. The firewall implies the opposite of violent, detectable boundary. So which is right? Physicists are split. Some argue firewalls must exist to preserve quantum mechanics. Others call it a sign that our theories are incomplete, missing a deeper truth about how gravity and quantum physics unite. The stakes couldn't be higher. If firewalls are real, they'd rewrite the rules of black holes, making them even more hostile than we thought. But if they're not, we might need a radical new framework to explain how information escapes black holes without violating quantum laws. Either way, this puzzle forces us to question the very nature of spacetime. Interestingly, the debate ties back to earlier secrets we've covered, like Hawking radiation and the information paradox. It shows how black holes keep pushing the boundaries of physics, revealing gaps in our knowledge. For now, the firewall remains unproven, a tantalizing what-if that keeps scientists awake at night. But that's the beauty of these cosmic enigmas. They refuse to let us settle for easy answers. Exploring another tantalizing mystery of supermassive black holes, let's venture into the realm of science fiction turned potential reality, the wormhole possibility. Could these cosmic behemoths actually serve as gateways to distant parts of the universe, or even other dimensions? The idea isn't just fantasy. Under extreme conditions, the warped space-time around a supermassive black hole might naturally form a traversable wormhole, bending the rules of physics as we know them. Here's how it could work. Wormholes, often called Einstein-Rosen bridges, are theoretical tunnels through space-time connecting two distant points. While general relativity allows for their existence, they'd require exotic matter with negative energy to stay open long enough for anything to pass through. Supermassive black holes, with their unimaginable gravitational pull, might just provide the perfect conditions for this. Their immense mass curves space-time so drastically that under certain circumstances, a bridge could form between their singularity and another point in the cosmos. But before you picture interstellar travel, there's a catch. The tidal forces near a black hole's event horizon are so strong they'd stretch any object into atoms, a process called spaghettification. Even if a wormhole existed, surviving the journey seems impossible. However, some physicists speculate that rapidly spinning supermassive black holes could create a gentler passage. Their rotation might twist spacetime into a stable enough configuration to allow safe transit, at least in theory. The key lies in something called the Kerr metric, which describes rotating black holes. Unlike their static counterparts, these cosmic whirlpools don't crush everything at their centers to a single point. Instead, they form a ring-shaped singularity. Some models suggest that passing through this ring could lead to another universe or a different part of our own, avoiding the infinite density at the core. It's a wild idea, but mathematically plausible under extreme conditions. What's even more fascinating is how this ties into quantum mechanics. The same quantum foam we discussed earlier, where tiny wormholes constantly blink in and out of existence, might get amplified near a supermassive black hole singularity. Under the right conditions, one of these microscopic tunnels could expand into a traversable bridge, though controlling it would require technology far beyond our current capabilities. Of course, we're still far from proving any of this. No observational evidence for wormholes exists yet, and the exotic matter needed to stabilize them remains purely theoretical. But the possibility keeps scientists intrigued. After all, if supermassive black holes can warp spacetime enough to stop time itself, why couldn't they bend it into a tunnel? The universe has surprised us before, and these cosmic mysteries remind us how much we have left to discover. This idea also ties back to earlier secrets we've explored, like time dilation near black holes and the holographic principle. It shows how interconnected these puzzles are, each one a piece of the grand cosmic tapestry. Whether or not wormholes exist in reality, their study pushes the boundaries of both physics and imagination, proving once again that supermassive black holes are far more than just celestial vacuum cleaners. They're the universe's ultimate laboratories. As we continue unraveling these cosmic enigmas, remember that every wild theory started as someone's what if. The line between science fiction and science fact has always been blurry when it comes to black holes. Who knows, the next breakthrough might come from staring into the abyss and finding it stares back with answers we never expected. Now let's turn our attention to an astonishing idea. Supermassive black holes might actually hold the history of their galaxies like cosmic archives. Imagine if these gravitational giants could tell us the story of every collision, every merger, and every dramatic encounter their host galaxies have endured over billions of years. Believe it or not, that's exactly what some scientists propose when they talk about the galactic DNA encoded in a black hole's spin and mass. Here's how it works. When galaxies collide, their central black holes eventually spiral toward each other, locked in a gravitational dance. As they merge, the resulting supermassive black hole gains mass and absorbs the angular momentum of its predecessors. The final spin and mass of the black hole become a fingerprint of that violent cosmic union. By studying these properties, astronomers can essentially replay the history of a galaxy's mergers, like reading chapters in a book written in gravity and motion. Take, for example, a black hole spinning at near light speed. Its rapid rotation might indicate it grew primarily by consuming gas from a steady, one-directional accretion disk over eons. On the other hand, a slower spinning black hole could be the product of multiple chaotic mergers, where collisions from random angles cancelled out some of its rotational energy. Even the mass itself holds clues. An unexpectedly heavy black hole might suggest a history of frequent galactic mergers, each one piling on more stellar material. But the story doesn't end there. Some of the most massive black holes we've observed, like those in the centers of galaxy clusters, show signs of repeated mergers over cosmic time. Their enormous masses and peculiar spins act like scars from past battles, hinting at a violent history of galactic cannibalism. In fact, researchers have used computer simulations to trace back these mergers, matching the predicted spin and mass of black holes to the turbulent histories of their host galaxies. What's truly fascinating is how this galactic DNA connects to secrets we've already explored. The spin of a black hole influences its jets and accretion disk, as we saw earlier, while its merger history might explain why some galaxies have multiple supermassive black holes lurking in their cores. This interplay between a black hole's past and its present behavior reveals just how deeply intertwined these cosmic titans are with the galaxies they call home. Of course, decoding this cosmic record isn't simple. Measuring the spin of a black hole, for instance, requires precise observations of how its gravity affects nearby stars and gas. But with advancements in telescopes and simulations, scientists are getting closer to reconstructing galactic histories from these gravitational fingerprints. So the next time you look at an image of a distant galaxy, remember, its central black hole isn't just a silent monster. It's a storyteller holding within its spin and mass the epic saga of collisions, feasts, and transformations that shaped its home. And as we learn to read these cosmic records, we're not just studying black holes, we're uncovering the autobiography of the universe itself. But here's where things get even more mind-bending. While we've seen how black holes preserve galactic histories, they also confront us with one of the greatest paradoxes in modern physics. Supermassive black holes sit at the crossroads between two seemingly incompatible worlds: Einstein's general relativity, which governs their immense gravity, and quantum mechanics, which should describe the behavior of particles at their tiniest scales. This collision of theories creates what scientists call the black hole information paradox, and it threatens to rewrite our fundamental understanding of reality. Consider what happens when matter falls into a black hole. According to Einstein's theory, that material is crushed into the singularity, its information seemingly lost forever from our universe. Yet quantum mechanics insists that information can never be truly destroyed. It might change form, but it can't vanish. This contradiction isn't just academic. It suggests one of these foundational theories must be incomplete when pushed to extremes. Stephen Hawking first highlighted this paradox when he discovered black holes emit radiation, now called Hawking radiation. At first glance, this evaporation seems to destroy information, violating quantum rules. Later, Hawking proposed that information might escape encoded in this radiation, but we still don't know exactly how. The debate has led to wild ideas, like black holes being surrounded by intense firewalls at their event horizons, or the notion that all swallowed information gets smeared across a black hole's surface like a cosmic hologram. What makes this even more perplexing is how supermassive black holes intensify the problem. Their vast event horizons stretch spacetime so dramatically that quantum effects near them could potentially warp reality itself. Some theories suggest information might leak out through subtle quantum connections between particles inside and outside the black hole, while others propose that black holes might eventually spit everything back out in some scrambled form, just over unimaginable timescales. This paradox isn't just about black holes, it's about the nature of spacetime and information at the most fundamental level. Solving it might require a theory of quantum gravity, the holy grail of modern physics that could unite relativity and quantum mechanics. Until then, supermassive black holes remain cosmic laboratories, pushing the boundaries of our knowledge and forcing us to rethink reality itself. Now let's turn our attention to one of the most baffling cosmic puzzles: galaxies that break all the rules by apparently missing their central supermassive black holes. Conventional wisdom tells us these gravitational giants should anchor nearly every large galaxy, yet astronomers keep stumbling upon dark galaxies that defy expectations. Take the case of Messier 33, a spiral galaxy in our cosmic neighborhood. Despite being one-third the size of the Milky Way, searches for a central black hole have come up empty. The same goes for several ultra-diffuse galaxies, those faint, wispy structures that somehow float through space without the dense cores we'd expect. These oddballs force us to reconsider how black holes and galaxies grow together. The mystery deepens when we examine galaxy formation theories. Most models suggest supermassive black holes and their host galaxies evolve in tandem, with the black hole's gravity influencing star formation while galactic gas feeds the black hole. But dark galaxies upend this symbiotic relationship. One possibility is that their black holes might exist but remain dormant, having exhausted nearby fuel long ago and now lurking undetectably quiet. Alternatively, some galaxies could form through rare pathways that skip black hole seeding entirely, perhaps via unusually gentle mergers that never concentrated enough matter to create one. Then there's the enigma of NGC 1277, a relic galaxy thought to preserve conditions from the early universe. It hosts a shockingly oversized black hole relative to its modest stellar population, suggesting black holes might sometimes form first and dictate galaxy growth rather than the other way around. If that's true, why do some galaxies like Messier 33 lack one entirely? the contradictions are piling up. What makes dark galaxies particularly tantalizing is that they might hold clues about the universe's primordial black holes, hypothetical objects formed in the chaos of the Big Bang. If such black holes exist, they could explain why some galaxies deviate from standard models. Or perhaps dark galaxies are the remnants of violent collisions where a black hole was ejected entirely, sent careening through intergalactic space by gravitational recoil. As telescopes grow more powerful, each new observation chips away at the mystery. The upcoming Nancy Grace Roman Space Telescope, for instance, could uncover hundreds more of these rule-breaking galaxies, helping us piece together whether they're cosmic exceptions or evidence of gaps in our theories. Until then, dark galaxies stand as humbling reminders that the universe still guards some of its deepest secrets tightly. Moving forward into another cosmic puzzle, let's explore the fascinating case of black hole nurseries, young galaxies where the supermassive black hole seems to take center stage before the galaxy itself has even fully formed. This defies our traditional understanding of galaxy evolution, where stars and galactic structures were thought to emerge first, providing the environment for a black hole to grow. But recent observations are flipping this script entirely. Take the galaxy CR7, one of the brightest and most distant galaxies ever observed, dating back to when the universe was less than 1 billion years old. At its heart lies a supermassive black hole so massive that it shouldn't have had enough time to form under conventional models. Even more baffling, the surrounding galaxy appears sparse and underdeveloped, as if the black hole arrived first and the stars are still playing catch-up. Scientists are now asking, did these black holes form directly from collapsing gas clouds in the early universe, skipping the typical seed stage entirely? Then there's the discovery of quasars in the cosmic dawn, active galactic nuclei so bright they outshine their host galaxies. These celestial powerhouses imply that supermassive black holes were already thriving when the universe was in its infancy, long before the galaxies around them had fully taken shape. This raises a radical possibility that some black holes didn't grow from smaller stellar remnants, but instead were born big through exotic processes we're only beginning to understand. One leading theory suggests that in the dense, turbulent conditions of the early cosmos, massive gas clouds could have collapsed directly into black holes without ever forming stars first, a phenomenon called direct collapse. These primordial black holes would have started with masses tens of thousands of times that of our Sun, giving them a head start in growing into the behemoths we see today. Another idea proposes that ultra-rapid accretion feeding at near maximum rates allowed small black hole seeds to balloon in size almost instantly in the chaotic early universe. What makes black hole nurseries so intriguing is their potential to rewrite galactic formation theories. If black holes truly formed first, they may have acted as gravitational anchors, pulling in matter and shaping the galaxies that eventually grew around them. This would flip the traditional view that galaxies dictate black hole growth. Observations with the James Webb Space Telescope are now uncovering more of these extreme young systems, each one offering clues about how the first supermassive black holes came to be. However these cosmic nurseries work, they remind us that the early universe was a far wilder and more inventive place than we ever imagined. Diving deeper into the cosmic life cycle, let's uncover one of the most mind-bending secrets of supermassive black holes. They might not be the ultimate endpoints we once thought. Instead, they could act as cosmic recyclers, eventually returning swallowed matter back to the universe in a process so slow and subtle it defies imagination. This phenomenon hinges on Hawking radiation, a theoretical prediction by physicist Stephen Hawking that suggests black holes aren't entirely black after all. Here's how it works. According to quantum mechanics, empty space isn't truly empty. Particle-antiparticle pairs constantly flicker in and out of existence, borrowing energy from the vacuum before annihilating each other in a flash. But near a black hole's event horizon, something extraordinary happens. If one of these particles falls in while the other escapes, the black hole effectively loses a tiny bit of mass. Over unimaginable timescales, think trillions upon trillions of years, this slow leak of energy causes the black hole to evaporate entirely. What was once a cosmic vacuum cleaner becomes a faint whisper of radiation, returning its stolen matter to the universe in the most ethereal way possible. Now, let's put this into perspective. A black hole with the mass of our Sun would take around 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros, a time span so vast it makes the current age of the universe look like a blink. But for supermassive black holes, the process is even slower. A typical galactic center behemoth, weighing in at millions or billions of solar masses, would take exponentially longer to fade away. By the time these giants start evaporating in earnest, the universe itself might be a cold, dark expanse with no stars left to shine. What's even more fascinating is what happens at the very end. As a black hole nears the final moments of its evaporation, the radiation isn't just a steady trickle, it becomes a runaway explosion. The last bursts of energy would release particles and light at incredible intensities, potentially seeding the cosmos with fresh material for future stars and planets. In a way, black holes could be the universe's ultimate conservationists, ensuring nothing is truly lost forever. This leads us to a startling implication. If Hawking radiation is real and experiments are still trying to confirm it, then every black hole, no matter how massive, has an expiration date. The supermassive monsters anchoring galaxies today will one day fade into nothingness, their energy dispersed back into the cosmic void. It's a poetic twist in the tale of these gravitational giants, transforming them from eternal prisons into temporary waystations in the grand cycle of matter and energy. Of course, this raises tantalizing questions. Could the particles emitted via Hawking radiation carry information about what fell into the black hole, solving the infamous information paradox? Some theories suggest they might, preserving the universe's quantum memory even as the black hole vanishes. Others propose that the radiation is entirely random, erasing any trace of the black hole's past meals. Either way, the idea that black holes participate in cosmic recycling challenges our deepest assumptions about gravity, quantum physics, and the fate of the universe itself. As we peer into the far future, one thing becomes clear: black holes aren't just destructive forces. They're part of a delicate cosmic balance where even the most voracious appetite eventually gives way to renewal. And that might be their greatest secret of all. Moving beyond the cosmic recycling we just explored, let's delve into another astonishing secret: supermassive black holes don't feed at a constant rate. Instead, they experience seasons much like Earth, with periods of intense activity and others of near dormancy. These cycles, spanning thousands or even millions of years, reveal a dynamic side to these gravitational giants that challenges our static perceptions. Picture a supermassive black hole at the heart of a galaxy, surrounded by a swirling buffet of gas, dust, and occasional unlucky stars. Just as our planet has winters and summers dictated by its orbit, a black hole's feeding frenzy ebbs and flows based on its cosmic environment. During its summer, the black hole gorges on nearby material, heating its accretion disk to unimaginable temperatures and unleashing brilliant jets of radiation. These active phases often coincide with galactic collisions or periods when dense gas clouds spiral inward, fueling the beast. But when supplies run low, perhaps because the black hole has cleared its immediate vicinity or neighboring stars have been flung away by gravitational interactions, the feast winds down. The accretion disk cools, jets fade, and the black hole enters a winter of relative quiet. Astronomers have observed this variability in real time. For instance, the supermassive black hole in the center of galaxy M87, famous for its iconic jet, has shown fluctuations in brightness over decades, hinting at these seasonal shifts. What's truly fascinating is how these cycles impact entire galaxies. During a black hole's active phase, the energy released can heat surrounding gas so intensely that it prevents new stars from forming, effectively putting a pause on galactic growth. Conversely, in quieter periods, cooler gas can condense into stars, sparking waves of stellar birth. This means supermassive black holes don't just sit idly at galactic centers. They actively shape their home's evolution through their feeding rhythms. The causes behind these seasons are as varied as the black holes themselves. Some may be triggered by external events, like a nearby galaxy passing too close and stirring up fresh material. Others could result from internal instabilities in the accretion disk, where clumps of gas fall inward in irregular bursts. There's even evidence that some supermassive black holes burp after large meals, expelling excess energy in powerful outbursts that temporarily shut down further feeding. Studying these cycles isn't just academic, it's key to understanding why some galaxies, like our Milky Way, have relatively quiet central black holes, while others, like quasars, shine with the light of a trillion stars. By piecing together the clues from X-ray observations, radio emissions, and even gravitational wave detectors, scientists are beginning to map the life cycles of these cosmic titans. So the next time you think of black holes as unchanging voids, remember, they have their own rhythms, their own seasons of hunger and hibernation. And just like the turning of the year shapes our world, these cycles mold the destiny of galaxies across the cosmos. Now let's shift our gaze to one of the most mind-bending secrets of supermassive black holes: their ability to outperform even the most powerful energy sources in the universe. Imagine a cosmic power plant so efficient it puts all human technology to shame. That's exactly what happens near the event horizon of these gravitational titans, where matter doesn't just vanish, it gets transformed into pure energy with staggering efficiency. Here's the jaw-dropping comparison. While nuclear fusion in stars, including our Sun, converts a mere 0.7% of mass into energy, supermassive black holes can achieve efficiencies up to 40%. That's nearly 60 times more effective than the process that lights up galaxies. How it all comes down to the extreme physics near the black hole's spinning edge, where space itself twists like a whirlpool. Picture matter spiraling inward through the accretion disk, accelerated to near light speed by the black hole's immense gravity. As particles collide and heat up to millions of degrees, something extraordinary happens. The black hole's rotation drags space-time along with it, creating a cosmic slingshot effect. This phenomenon, known as frame dragging, extracts energy directly from the black hole's spin and transfers it to the surrounding matter. The result: a significant portion of the infalling mass gets converted into radiation and jet energy before it ever crosses the event horizon. Scientists quantify this using something called the Penrose process, named after physicist Roger Penrose, who first described it. In simple terms, if you could mine a black hole by dropping matter into its ergosphere, the region just outside the event horizon where frame dragging is strongest, you could theoretically recover up to 40% of that matter's mass as usable energy. Compare that to hydrogen bombs or even hypothetical fusion reactors on Earth, which tap into less than 1% of matter's potential, and you start to grasp why black holes are the ultimate energy converters. Real-world examples abound. Take quasars, the brilliant cores of distant galaxies powered by supermassive black holes. A single quasar can outshine thousands of galaxies combined, emitting more energy in 1 second than our Sun will in its entire 10 billion-year lifetime. This isn't just raw power, it's precision engineering on a cosmic scale, where gravity, magnetism, and particle physics collaborate to squeeze every last drop of energy from matter. What's truly revolutionary is that this process doesn't violate Einstein's famous equation E equals mc squared. It maximizes it. While stars like our Sun fuse light elements through relatively wasteful processes, black holes exploit relativity itself to achieve unparalleled efficiency. Even Hawking radiation, the slow energy leakage from tiny black holes, follows this principle of extreme energy conversion, though on vastly longer timescales. So why does this matter beyond cosmic curiosity? Understanding these mechanisms could one day inspire revolutionary energy technologies. While we're light years from harnessing black hole physics, the principles behind their efficiency, like accelerating particles through magnetic fields or extracting rotational energy, already influence cutting-edge research in plasma physics and fusion energy. Next time you see images of a quasar's dazzling jets or an active galaxy's radiant core, remember, you're witnessing nature's ultimate power plant in action, where the laws of physics are pushed to their limits to create something truly extraordinary. Now let's journey into an idea that sounds like science fiction, but might just be the future of cosmic travel: how supermassive black holes could serve as the ultimate navigation beacons for civilizations exploring the galaxy. Picture this: you're a starship captain navigating the vast, star-strewn ocean of the Milky Way. The problem? Traditional star maps won't cut it when you're light years from home, where familiar constellations twist into unrecognizable shapes due to the galaxy's rotation. But there's one celestial landmark that stands unchanging: the gravitational giants at the heart of galaxies. Supermassive black holes are nature's perfect lighthouses. Unlike stars, which move, evolve, and eventually die, these colossal objects sit motionless at galactic centers, their immense gravity anchoring entire galaxies. Their fixed positions make them ideal reference points for plotting courses across interstellar distances. Think of them as cosmic versions of GPS satellites, except instead of radio signals, they emit predictable gravitational waves and radiation patterns that could be detected across thousands of light years. Here's how it might work. Advanced civilizations could map the unique spin signatures and gravitational wave fingerprints of different supermassive black holes. Each one spins at a distinct rate, warping spacetime around it in a pattern as identifiable as a barcode. By triangulating signals from multiple black holes, say Sagittarius, a star in our Milky Way, and the black hole in Andromeda, a ship's navigation system could pinpoint its location with extraordinary precision, even in the void between galaxies. But the real genius lies in the black hole's stability. Their enormous mass means they're unaffected by the chaotic motions of stars and gas clouds. While pulsars, spinning neutron stars often proposed as navigation aids, eventually slow down or get knocked off course by cosmic events, a supermassive black hole's behavior remains constant over millions of years. Some scientists speculate that the plasma jets shooting from active black holes could serve as literal cosmic arrows, their consistent orientations providing directional markers visible across intergalactic distances. There's historical precedent too. On Earth, early navigators used Polaris, the North Star, because its fixed position above the pole made it reliable. Supermassive black holes are the Polaris of galactic travelers, except instead of guiding ships across oceans, they'd guide vessels between stars. What's truly mind-blowing? We might already have evidence of this concept in nature. Some theories suggest migratory animals like whales or birds use Earth's magnetic field for navigation. Imagine an alien species evolving near a black hole's accretion disk, developing biological sensors tuned to its gravitational pulses the way sharks detect electric fields. While humanity is far from needing such technology, the principles could shape future deep space missions. Probes traveling beyond our solar system might one day calibrate their positions using the rhythmic gravitational waves emitted by merging black holes, a celestial drumbeat echoing across the cosmos. Until then, supermassive black holes remain the universe's most reliable signposts, silently marking the crossroads of the galaxy for any civilization advanced enough to read their signals. And speaking of signals, our next secret reveals something even more astonishing: how these gravitational titans might hold the key to a galaxy-wide communication network. But that's a story for another moment. Now let's take a step into the realm of theoretical physics where the unimaginable becomes possible. Imagine harnessing the sheer gravitational might of a supermassive black hole to bend time itself not just as a thought experiment but as a potential reality. This is the mind-bending concept behind time travel via supermassive black holes, and while it might sound like pure science fiction, it's rooted in the very real principles of Einstein's theory of relativity. At the heart of this idea lies a phenomenon called time dilation, the stretching of time caused by extreme gravity. Near a supermassive black hole, gravity is so intense that it warps spacetime to an extraordinary degree. Picture an astronaut orbiting close to the event horizon. From their perspective, time would pass normally, but for someone watching from a safe distance far away, the astronaut's clock would appear to tick agonizingly slow. The closer the orbit, the more dramatic the effect. After just a few hours near the black hole, years or even decades could pass for the rest of the universe. This isn't just speculation. We already observe time dilation on a smaller scale. GPS satellites orbiting Earth, for example, have to account for tiny time differences caused by our planet's gravity. But near a supermassive black hole, the effect is millions of times stronger. Scientists have calculated that orbiting Sagittarius A star, the black hole at our galaxy's center, for just 1 year could mean returning to an Earth that has aged several decades. It's a one-way ticket to the future, no paradoxes, no breaking physics, just the universe's natural clockwork operating in extreme conditions. The mechanics behind this are fascinating. As an object approaches the black hole's event horizon, gravitational redshift comes into play. Light struggling to escape the black hole's pull loses energy, stretching its wavelength and slowing its frequency. This redshift effect directly impacts how time is perceived. An observer watching from afar would see the astronauts' movements become sluggish, their signals arriving at longer and longer intervals until they seem frozen in time entirely. But here's the catch: surviving the trip is another matter entirely. Tidal forces near a black hole would stretch anything venturing too close into spaghetti-like strands, a process colorfully known as spaghettification. To use a supermassive black hole as a time machine, you'd need to orbit at just the right distance, close enough to experience significant time dilation, but far enough to avoid annihilation. Some theories suggest rapidly spinning black holes might offer safer orbits due to their warped space-time geometry, creating pockets where time slows dramatically without the lethal stretching. What does this mean for the future? While humanity lacks the technology to attempt such a journey today, the principle itself opens doors to profound possibilities. Imagine civilizations far more advanced than ours using black holes as natural time capsules. A society facing extinction could send a crew on a carefully calculated orbit, returning centuries later to a rejuvenated galaxy. Or consider deep space missions where astronauts age minimally compared to those back home, allowing them to witness the distant future firsthand. And before you dismiss this as pure fantasy, remember that time dilation has been tested and confirmed in countless experiments. The universe doesn't just allow for time travel into the future, it demands it under the right conditions. Supermassive black holes are those conditions taken to the extreme, nature's own time machines lurking in the hearts of galaxies. Which brings us to our next secret, one that pushes the boundaries of physics even further. What if these cosmic titans aren't just anchors of gravity, but gateways to something even more extraordinary? Stay tuned, because the answer might just rewrite our understanding of reality itself. Now let's shift our gaze to an idea so futuristic it could redefine how civilizations communicate across the cosmos. Picture this: gravitational waves rippling through space-time like cosmic Morse code, carrying messages between stars. This is the radical concept behind the black hole internet, where merging supermassive black holes might one day serve as nature's ultimate transmitters. Gravitational waves, those faint wrinkles in spacetime first detected in 2015, aren't just scientific curiosities. When two supermassive black holes spiral toward collision, they generate waves with the energy of billions of supernovae, vibrating the very fabric of the universe. These waves travel at light speed, unimpeded by dust, gas, or magnetic fields that scramble traditional electromagnetic signals. For an advanced civilization, this could be the perfect communication medium. Think of it like tapping on a spider's web. Just as vibrations travel cleanly across silken threads, gravitational waves preserve their information across millions of light years without degrading. A civilization could encode data in the specific frequency patterns of artificial black hole mergers, perhaps using smaller black holes as precise instruments. The resulting waves would carry this information across galactic distances, bypassing the limitations of light-based systems that get absorbed or distorted by interstellar material. The engineering challenges are staggering, but not impossible in principle. To create detectable signals, a civilization would need to manipulate black holes with masses thousands of times our Sun, carefully nudging them into controlled collisions. This might require technologies harnessing dark matter or manipulating spacetime itself, feats far beyond our current capabilities, yet the theoretical foundation exists. The LIGO Observatory has already proven we can detect gravitational waves from black hole mergers occurring over 1 billion light-years away. Scale that sensitivity up, and galaxy-wide messaging becomes plausible. What would such a network look like? Imagine relay stations around supermassive black holes in key galaxies, each acting as a node in an interstellar communications web. Messages could hop between these nodes via precisely timed mergers, creating a lag-free network where news travels at the speed of gravity itself. Unlike radio signals that take centuries to cross the Milky Way, gravitational wave messages might traverse the same distance in real time from the sender's perspective, thanks to relativity's time compression effects near black holes. There's even a tantalizing natural precedent. Some astrophysicists speculate that the regular spacing of certain supermassive black hole pairs might not be coincidental. Could these be remnants of an ancient communication network left by a long-gone civilization? While purely speculative, it's a fascinating lens through which to view these cosmic anomalies. Of course, this raises profound questions. Would messages encoded in spacetime vibrations be secure from eavesdropping? Could different civilizations develop compatible encoding protocols? And most intriguingly, have we already detected such signals without realizing it? As our gravitational wave observatories grow more sophisticated, we might uncover patterns that don't fit natural merger models' hints of intelligent design in the cosmic static. This isn't just science fiction. The same physics enabling us to detect colliding black holes could, in theory, be harnessed for communication. It's a reminder that the universe's most violent phenomena might also be its most useful tools. While humanity is millennia away from such feats, the mere possibility expands our vision of what advanced civilizations might achieve, turning spacetime itself into their information superhighway. Which brings us to our next revelation, one that challenges everything we thought we knew about black holes and the fundamental nature of reality. Stay tuned, because the truth might be stranger than anything we've imagined so far. Now, let's venture into the quantum realm, where even the most established black hole theories get turned on their head. For decades, physicists have clung to the no-hair theorem, the idea that black holes can be described by just 3 simple properties: mass, spin, and charge. But groundbreaking research is now suggesting there might be more to these cosmic enigmas, tiny, quantum-scale hair, that could rewrite our understanding of black hole physics. This revelation starts with a puzzle. If black holes truly have no hair, then all information about what falls into them would be lost forever. That contradicts a fundamental principle of quantum mechanics. Information can't just vanish. To resolve this paradox, scientists are probing the chaotic boundary where quantum effects meet gravity's crushing dominance. New calculations suggest that as particles approach a black hole's event horizon, their quantum fields might leave faint imprints like strands of hair on the black hole's surface. These imprints could preserve details about what was swallowed, encoded in subtle disturbances in spacetime itself. Imagine dropping a book into a black hole. According to classical physics, it's gone, no traces left, but quantum hair theory proposes that the book's information isn't destroyed. Instead, it's scrambled into microscopic fluctuations on the event horizon, a kind of quantum fingerprint. This isn't just theoretical elegance, it's a potential solution to the infamous black hole information paradox that's baffled physicists since Stephen Hawking first raised it. The implications are staggering. If quantum hair exists, black holes aren't the simple, bald objects we thought. They'd be intricate cosmic archives, their surfaces buzzing with encoded data. Detecting this would require instruments far beyond today's technology, perhaps devices sensitive enough to measure subtle changes in a black hole's gravitational field or quantum emissions from its edge. Some researchers even speculate that future gravitational wave observatories might catch hints of these quantum imprints during black hole mergers, where horizons stretch and twist in ways that could reveal hidden structures. Critics argue that quantum hair might be too faint to ever detect, buried under overwhelming gravitational noise. But proponents counter that if the universe preserves information, as quantum mechanics insists, then these hairs must exist, even if they're incredibly subtle. It's a debate that cuts to the heart of whether gravity and quantum mechanics can ever be reconciled. What makes this research thrilling is that it's not just about black holes. If quantum hair is real, it could point toward a unified theory of physics, a framework that finally merges Einstein's gravity with the quantum world. Every strand of this hypothetical hair represents a thread connecting the very large to the very small, a clue to how the universe stores and processes information at the most fundamental level. So while we can't yet see these quantum hairs, their potential existence reminds us that black holes are far stranger than any theorem could capture. They might not be the smooth, featureless pits we imagined, but dynamic, information-rich objects, cosmic puzzles waiting to be unraveled. And with that, we're ready to dive into another mystery, one that questions whether black holes might force us to rewrite the laws of physics altogether. Now, let's tackle one of the most perplexing puzzles in modern physics, the black hole information paradox. This isn't just a minor glitch in our theories. It's a full-blown crisis that threatens to upend everything we know about quantum mechanics and gravity. At its core, the paradox forces us to confront a burning question. What happens to information when it falls into a black hole? According to quantum mechanics, information is sacred. It can't be created or destroyed, only transformed. Every particle, every interaction leaves a trace, a kind of cosmic paper trail. But black holes, with their immense gravity, seem to break this rule. When matter crosses the event horizon, it's supposedly gone forever, its information irretrievably lost. Stephen Hawking's groundbreaking work in the 1970s suggested that black holes slowly evaporate, emitting radiation over unimaginable timescales. But here's the catch: Hawking radiation appears random, carrying no information about what fell in. If that's true, then the universe has a serious accounting problem. Physicists have wrestled with this dilemma for decades, proposing wild solutions that range from the elegant to the downright bizarre. One leading idea is the holographic principle, which suggests that all the information swallowed by a black hole isn't lost but instead encoded on its surface like a cosmic hologram. Imagine a dropped glass shattering on the floor. From a distance, the pieces seem chaotic, but up close, you could theoretically reconstruct the original glass. Similarly, the holographic principle argues that the event horizon preserves information in a scrambled, two-dimensional form, waiting to be decoded. Another radical proposal involves baby universes. Some theories suggest that black holes might spawn entirely new universes inside them, with the ingested information flowing into this nascent cosmos. While this sounds like science fiction, it's a legitimate attempt to reconcile the paradox. Yet others argue for firewalls, searing walls of energy at the event horizon that destroy incoming matter but somehow preserve its information. Each of these ideas pushes the boundaries of physics, demanding revisions to quantum theory or even general relativity. The stakes couldn't be higher. If information truly vanishes in black holes, we'd need to rewrite quantum mechanics from the ground up. But if it's preserved in some exotic way, we might finally uncover the missing link between gravity and the quantum world. Current experiments like gravitational wave detectors are searching for subtle clues, anomalies in black hole mergers or echoes in Hawking radiation that could hint at information preservation. What makes this paradox so thrilling is that it's not just about black holes, it's about the fundamental nature of reality. Solving it could reveal how space-time emerges from quantum entanglement or how the universe stores information at the most basic level. Whether through holograms, firewalls, or something even stranger, one thing is clear: black holes aren't just cosmic vacuum cleaners. They're laboratories for the most profound questions in physics, forcing us to rethink the very laws that govern existence. And with that, we're stepping into another mind-bending mystery, one that explores whether black holes might hold the key to unlocking even grander cosmic secrets. Now let's journey back to the dawn of time, when the universe was a vastly different place, a cosmic nursery where the first seeds of supermassive black holes may have taken root in the form of something even stranger: dark stars. These aren't the twinkling lights we see today, but hypothetical giants powered not by nuclear fusion, but by the annihilation of dark matter. Picture a star hundreds of thousands of times more massive than our Sun, glowing faintly with eerie, otherworldly light as dark matter particles collide and vanish within its core. These dark stars could have been the universe's first true monsters, collapsing directly into the supermassive black holes we see at galactic centers today. The idea of dark stars is more than just a fascinating what-if. It could solve one of cosmology's biggest headaches: how supermassive black holes grew so enormous so quickly. In the early universe, mere hundreds of millions of years after the Big Bang, we've spotted quasars, bright beacons powered by black holes already weighing billions of suns. For them to reach that size, they'd need a head start, something far more massive than the stellar black holes formed from dying stars. Enter dark stars. If they existed, their sheer size would let them collapse directly into black holes with masses thousands or even millions of times that of our Sun, skipping the slow growth phase entirely. But how would these dark stars form? Imagine clouds of primordial gas, rich in dark matter, collapsing under gravity. As ordinary matter clumps together, dark matter particles, hypothetically weakly interacting massive particles, or WIMP, get trapped in the star's core. When they collide, they annihilate, releasing energy that counteracts gravity's inward pull. The result, a star that can grow to staggering sizes without ever igniting nuclear fusion, stabilized by this dark energy source. Over time, as dark matter is depleted, the star's core collapses, triggering a runaway chain reaction that births a black hole with a ready-made feast of surrounding gas to fuel its growth. The legacy of dark stars might still be visible today. Some astronomers suggest that supermassive black holes with unusually high spins or peculiar growth patterns could be the fingerprints of these primordial giants. Others are searching for faint, distant objects in the early universe that match dark stars' predicted glow. While we haven't found definitive proof yet, the next generation of telescopes, like the James Webb Space Telescope, could spot their telltale signatures: redshifted light from an era when the cosmos was young and dark stars may have ruled. This isn't just about solving a cosmic mystery. If dark stars existed, they'd reshape our understanding of dark matter itself. Their formation would require dark matter to interact in ways we've never observed, hinting at entirely new physics beyond our current models. They'd also rewrite the story of galaxy formation, suggesting that the first black holes didn't just influence their galaxies, they may have built them from the ground up. So while dark stars remain elusive, their potential connection to supermassive black holes offers a thrilling glimpse into how the universe's most enigmatic structures might have begun. And with that, we're ready to explore another puzzle: how these gravitational giants might bend not just space, but the very fabric of reality itself. Now, let's shift our gaze to one of the most mind-bending phenomena in the cosmos, where supermassive black holes don't just consume light, they bend and magnify it like cosmic magnifying glasses. This is gravitational lensing, a dramatic demonstration of Einstein's theory of relativity in action. Picture a black hole so massive that its gravity warps the very fabric of space around it. When light from a distant star or galaxy passes close by, it doesn't travel in a straight line. Instead, it follows the curved spacetime, bending around the black hole like a car navigating a hairpin turn. The result, a natural telescope where the black hole's gravity amplifies and distorts the light of objects lying far behind it. What makes this even more fascinating is the variety of lensing effects we observe. Sometimes a single background galaxy appears as multiple images around the black hole, stretched into arcs or even complete rings known as Einstein rings. These ghostly halos of light form when the alignment between the black hole, the distant object, and our telescopes is just right. Other times, the lensing effect brightens the background object dramatically, allowing us to see galaxies that would otherwise be too faint to detect. It's as if the universe handed us a free upgrade to our observational power, all thanks to the extreme gravity of these invisible giants. One of the most famous examples lies in the galaxy cluster Abell 68. Here, a supermassive black hole's gravity has twisted a background galaxy into a surreal, mirrored arc, a cosmic funhouse reflection. But lensing isn't just about pretty pictures. Scientists use this effect to weigh black holes with incredible precision. By measuring how much the light bends, they can calculate the mass of the black hole causing the distortion. It's like watching a bowling ball sink into a mattress and using the dip it creates to guess its weight. Gravitational lensing also gives us a window into the early universe. Some of the most distant galaxies ever observed were spotted only because a foreground black hole magnified their light. Without this natural zoom lens, their signals would have been lost in the cosmic background noise. Even more intriguing, lensing can reveal dark matter's distribution around black holes, as the invisible stuff contributes to the bending of light. It's a reminder that these gravitational titans don't exist in isolation, they're woven into the larger cosmic web. But the real magic happens when we combine lensing with other observations. For instance, when a supermassive black hole's jets are lensed, astronomers can map their structure in unprecedented detail. Or consider microlensing, where smaller, transient brightening events betray the presence of rogue black holes drifting between stars. Each of these phenomena peels back another layer of mystery, showing how black holes shape not just their immediate surroundings, but our very view of the universe. So the next time you see an Einstein ring or a stretched galactic mirage, remember, you're witnessing space-time itself being sculpted by gravity's relentless pull. And with that, we're ready to peer even further into the future, to a time when these cosmic leviathans face their own astonishing fate. Now, let's journey far into the future, a future so distant it's almost unimaginable. Even the mightiest supermassive black holes, those seemingly eternal rulers of galactic centers, aren't immune to the slow march of time. Thanks to a revolutionary idea proposed by Stephen Hawking, we now know these cosmic giants have an expiration date. But don't expect fireworks or dramatic collapses. Their end comes not with a bang, but with a whisper spread over timescales that dwarf the current age of the universe. Hawking radiation, the subtle process sealing their fate, arises from quantum effects near the event horizon. Imagine particle-antiparticle pairs constantly popping in and out of existence in empty space. When this happens right at the edge of a black hole, one particle can fall in while the other escapes, stealing a tiny bit of the black hole's mass. Over unimaginable eons, this slow leak causes even supermassive black holes to evaporate. The bigger the black hole, the longer it takes. A typical galactic center monster might take 10 to the power of 100 years, that's a 1 followed by 100 zeros, to completely vanish. But here's where things get eerie. As evaporation progresses, the process speeds up. In their final moments, these once mighty black holes become incredibly hot, releasing energy equivalent to billions of nuclear bombs in a last burst of radiation before disappearing completely. Picture the universe's last supermassive black hole, isolated in an ocean of darkness, giving off one final glow before winking out of existence. It's a lonely end for objects that once dominated the cosmic landscape. This evaporation timeline raises profound questions. By the time the last black holes fade, the universe will be so old that stars will have burned out, galaxies will have dispersed, and even protons. The building blocks of matter may have decayed. The cosmos could enter a cold, dark era where black hole remnants are the only remaining structures. Some theories suggest these evaporating black holes might leave behind exotic Planck mass relics, hypothetical particles containing the last traces of their information. Others propose they vanish without a trace, erasing all evidence of their existence. Interestingly, Hawking radiation isn't just about destruction. It hints at a cosmic recycling program. Every particle emitted carries energy once locked inside the black hole, returning it to the universe in new forms. In a way, black holes might be the ultimate recyclers, converting swallowed stars and gas into radiant energy over trillions of years. Some speculative models even suggest this process could seed future universes, with evaporating black holes acting as cosmic reset buttons. Of course, all this rests on our current understanding of physics. Quantum gravity theories might rewrite parts of this story. Could black holes leave behind wormholes instead of evaporating entirely? Might information trapped inside somehow survive? These puzzles remind us that even in their demise, supermassive black holes challenge our grasp of reality. So while we won't be around to witness it, the ultimate fate of these gravitational titans paints a humbling picture. They teach us that nothing in the universe, no matter how powerful, lasts forever. And with that cosmic lesson, we're ready to explore how black holes might hold the key to something even grander, the holographic nature of reality itself. Now, let's shift our gaze to one of the most mind-bending ideas in modern physics, the holographic principle. Imagine the event horizon of a supermassive black hole not just as a point of no return, but as a cosmic hard drive, storing every bit of information that ever fell inside. This isn't science fiction. It's a serious theory suggesting that our three-dimensional reality might be encoded on a two-dimensional surface like a hologram. The idea stems from a paradox that baffled physicists for decades. According to quantum mechanics, information can never be destroyed, but black holes, with their insatiable appetites, seem to violate this rule by swallowing everything: stars, gas, even light, without leaving a trace. Enter the holographic principle. It proposes that the information isn't lost. Instead, it's imprinted on the black hole's event horizon in tiny, Planck-sized pixels. Picture it like a cosmic fingerprint where every atom, every photon that crosses the boundary leaves a unique mark. This concept flips our understanding of space and reality. Normally, we think of volume: the more space something occupies, the more information it can hold. But the holographic principle suggests that the true information capacity of a region isn't determined by its volume, but by its surface area. For a black hole, this means all the complexity of what's inside the swirling gases, the mangled stars, could be entirely described by data stored on its outer shell. It's as if the universe is projecting a 3D movie from a 2D screen with the event horizon as the projector. How does this work in practice? Think of a falling astronaut. From our perspective outside the black hole, they never quite cross the horizon due to time dilation. Instead, their image freezes, smears, and fades, encoding their information on the surface like a photograph burning into film. Meanwhile, from the astronaut's perspective, they plunge through unimpeded. Both views, outsider and insider, must be true, creating a paradox resolved only if the horizon acts as a hologram. The implications are staggering. If true, it means the entire universe might operate like a hologram, with our 3D experience emerging from a 2D boundary we can't see. Some theories even suggest that the universe's information could be stored on a distant cosmological horizon far beyond our observation. Supermassive black holes, with their immense event horizons, become natural laboratories to test this idea. But why does this matter beyond theoretical curiosity? Because it could be the key to unifying gravity and quantum mechanics. Black holes sit at the crossroads of these two theories, and the holographic principle offers a way to reconcile them. If space-time is truly a hologram, then the fabric of reality might be woven from quantum bits we're only beginning to understand. As we peel back these layers, one thing becomes clear. Supermassive black holes aren't just cosmic vacuum cleaners. They're Rosetta Stones holding clues to the deepest secrets of existence. And with that, we're ready to explore how civilizations, far more advanced than ours, might one day harness these unfathomable powerhouses. Now, let's venture into the realm of pure speculation where science meets imagination. Picture a civilization so advanced that it doesn't just observe supermassive black holes but uses them. We're talking about a Kardashev Type 3 civilization, one capable of harnessing the energy of an entire galaxy. And what better power source than the universe's ultimate energy factory, a supermassive black hole? First, consider the sheer scale of energy available. A spinning black hole converts mass into energy with mind-blowing efficiency, up to 40%, compared to a paltry 0.7% from nuclear fusion. That's like comparing a campfire to a supernova. Advanced beings could tap into this through mechanisms like the Penrose process, where they drop matter into the black hole's ergosphere, the region just outside the event horizon where spacetime itself is dragged into rotation. By splitting the infalling matter, they could steal a portion of the black hole's rotational energy, harvesting power on an unimaginable scale. But why stop there? A truly advanced civilization might build a Dyson sphere not around a star, but around the black hole itself, a megastructure we could call a black hole battery. They could capture the intense radiation from the accretion disk or even direct the relativistic jets as cosmic particle beams for interstellar engineering. Imagine using those jets like intergalactic blowtorches to reshape star systems or propel spacecraft at near light speeds. Then there's the wilder possibility, using black holes as quantum computers. The holographic principle we just discussed suggests black holes store information on their event horizons. What if an advanced civilization could program that data? By manipulating the horizon's quantum states, they might perform calculations that make our fastest supercomputers look like abacuses. The black hole becomes not just a power source but a cosmic superprocessor. Of course, this raises fascinating questions. How would such beings communicate? Gravitational waves from black hole mergers could serve as a galaxy-wide messaging system, ripples in spacetime carrying encoded information across millions of light years. Or perhaps they'd use the black hole's extreme gravity as a lens, bending light to create a natural telescope for observing distant events. But here's the most tantalizing thought. If these civilizations exist, why haven't we detected them? Maybe their technology operates on scales we can't yet perceive. Or perhaps they've transcended physical forms altogether, uploading their consciousness into the very fabric of spacetime near black holes. While this remains speculative, it forces us to confront the limits of our imagination. Supermassive black holes aren't just celestial oddities. they could be the ultimate tools for civilizations mastering the cosmos. And as we ponder these possibilities, we're reminded that the universe's greatest mysteries might not just exist out there, they might think. Now, let's push the boundaries of imagination even further. Could supermassive black holes be more than just cosmic powerhouses? Some daring theories suggest they might serve as gateways, bridges to entirely different universes. This is the realm of multiverse physics, where the lines between science and science fiction blur in the most thrilling ways. At the heart of this idea lies the concept of wormholes. According to Einstein's equations, the extreme gravity of a black hole could, in theory, warp spacetime so severely that it connects to another point in the cosmos, or even another universe altogether. Picture a cosmic subway tunnel with a supermassive black hole as the entrance and a hypothetical white hole as the exit, spewing out matter somewhere entirely unknown. While we've never observed a white hole, the math allows for their existence, making this a tantalizing possibility. But here's where it gets even wilder. Some physicists propose that the singularity at a black hole's core, the point where density becomes infinite, might not be a dead end. Instead, it could be a doorway. In certain multiverse models, like those inspired by string theory, our universe might be one brain floating in a higher dimensional space. A supermassive black hole's singularity could puncture this brain, linking it to another. Imagine our universe as a sheet of paper and the black hole as a pinprick that connects it to another sheet entirely. Of course, there's a catch. Even if such portals exist, surviving the trip is another matter. The tidal forces near a black hole's event horizon would spaghettify any known material, and the singularity itself remains a physics-breaking mystery. But some theories suggest that rotating black holes like the spinning supermassive ones we've discussed might offer a smoother passage. Their inner structure could hypothetically contain a K-ring singularity, which some models describe as a navigable tunnel rather than a destructive point. Why does this matter? If black holes truly are multiverse gateways, they'd redefine our understanding of reality. They could explain where the information swallowed by black holes truly goes, or even provide a mechanism for the birth of new universes. Some cosmologists speculate that our own universe might have emerged from a black hole in another cosmos, a mind-bending idea known as cosmological natural selection. While these ideas remain speculative, they challenge us to think bigger. Supermassive black holes might not just dominate galaxies, they could be the universe's ultimate connectors, threading the needle between realities. And as we peer into their inky depths, we're left wondering, if portals to other worlds exist, what or who might be on the other side? Now, let's venture into one of the most speculative yet fascinating frontiers of black hole science. The idea that these cosmic behemoths might hold clues to understanding consciousness itself. At first glance, connecting the dots between supermassive black holes and the nature of awareness seems like science fiction, but some bold theories suggest there could be a profound link hiding in the math. Imagine the event horizon of a black hole not just as a boundary of no return, but as a vast information processing surface. According to the holographic principle, all the data about what falls into a black hole might be encoded on its horizon like a cosmic hard drive. Now, here's where it gets wild. Some theorists propose that this information processing could resemble the neural networks in our brains. Just as our neurons fire and create patterns that give rise to thoughts, the quantum fluctuations at a black hole's edge might form complex, self-organizing structures. Could this mean black holes are, in some sense, conscious? One controversial hypothesis, inspired by quantum physics, suggests that consciousness isn't just a product of biology, but a fundamental feature of the universe. In this view, black holes, with their ability to store and transform information, might play a role in a grander cosmic mind. It's a stretch, yes, but consider this: black holes and brains both operate on feedback loops. Just as our thoughts emerge from the interplay of billions of neurons, a black hole's behavior emerges from the chaotic dance of particles at its horizon. Of course, there's no direct evidence for this, and mainstream science remains skeptical, but the speculative beauty lies in the questions it raises. If a black hole's information dynamics mimic conscious processes, could the universe itself be wired for awareness? Some even speculate that advanced civilizations might harness black holes as quantum computers, tapping into their processing power to simulate realities or communicate across dimensions. While these ideas push the limits of credibility, they remind us how much we still don't understand. Black holes challenge not just our physics, but our philosophies, forcing us to ask whether the universe is merely a cold machine or something far more mysterious. As we unravel these enigmas, we might find that the line between the cosmic and the conscious is thinner than we ever imagined. Now, let's bring our cosmic journey to its most breathtaking conclusion, the final revelation that ties everything together. Supermassive black holes aren't just cosmic oddities or galactic dictators. They might actually hold the key to solving physics' greatest mystery, a unified theory that bridges the gap between Einstein's gravity and the quantum world. Picture this: for over a century, scientists have struggled to reconcile general relativity, which governs the vast scales of space-time, with quantum mechanics, the rules of the subatomic realm. These two frameworks work flawlessly in their own domains but clash violently when forced together. Enter supermassive black holes. These extreme objects sit right at the crossroads of both worlds. Their immense gravity warps space-time like no other, while their event horizons where quantum effects become unavoidable force the two theories to interact. Here's where it gets groundbreaking. The holographic principle, which we touched on earlier, suggests that all the information inside a black hole is somehow encoded on its surface. This bizarre idea hints at a deeper truth, that our three-dimensional universe might actually be projected from a two-dimensional boundary, much like a hologram. If true, this could be the missing link between gravity and quantum physics. Some physicists believe that by studying how information behaves at a black hole's horizon, we might uncover the fundamental language of reality itself. But the clues don't stop there. The famous black hole information paradox, where information seemingly vanishes forever, has forced theorists to rethink the very nature of space and time. Solutions to this puzzle, like Hawking radiation or the idea of firewalls, all point toward radical new physics. Some even propose that spacetime itself might emerge from entangled quantum particles, with black holes acting as cosmic laboratories where this process is magnified. And then there's the mysterious connection to dark energy. Recent studies suggest that the growth of supermassive black holes could be tied to the universe's accelerating expansion. If confirmed, this would mean these cosmic giants aren't just passive inhabitants of galaxies but active players in shaping the fate of the cosmos. So what does all this mean? Supermassive black holes might be nature's ultimate Rosetta Stone, a cosmic cipher that could finally translate between gravity and quantum mechanics, space and time, even existence and information. They challenge us to think bigger, to question deeper, and to imagine that the answers to physics' toughest questions might be lurking in the darkest corners of the universe. As we stand on the edge of this revelation, one thing is clear: the study of supermassive black holes isn't just about understanding these enigmatic objects. It's about rewriting the rules of reality itself, and who knows, the next great leap in physics might not come from a particle collider or a telescope, but from staring into the abyss and letting the abyss stare back. As we wrap up this cosmic journey through 50 astonishing secrets of supermassive black holes, let's take a moment to see how these mind-bending revelations fit together like pieces of an infinite puzzle. From their invisible dominance at galactic centers to their bizarre connections with quantum physics, each secret we've uncovered peels back another layer of their mystery, revealing just how much we still have to learn. Think about it. These cosmic titans don't just shape galaxies, they challenge the very foundations of our understanding. They warp time, shred stars, and might even hold the key to unlocking a unified theory of everything. The more we study them, the more they push the boundaries of human knowledge, forcing us to rethink physics, cosmology, and even the nature of reality itself. But here's the thrilling part: we're only scratching the surface. Imagine what future discoveries might reveal. Will we finally solve the information paradox? Could supermassive black holes prove the existence of wormholes or other dimensions? Might they help us crack the code of dark energy? Every unanswered question is an invitation to explore further, to keep pushing the limits of what we know. Now, we'd love to hear from you. Which secret blew your mind the most? Was it the way these black holes control entire galaxies, or the eerie possibility that they might be cosmic holograms? Drop your favorite in the comments below. Let's geek out about the universe's greatest enigmas together. And if you've enjoyed this deep dive into the abyss, don't forget to hit that like button and subscribe for more mind-expanding space mysteries. Hit the notification bell so you never miss an upload. Who knows, the next big cosmic revelation could be just one video away. Until then, keep looking up, and remember, the universe's wildest secrets are still waiting